Okay, all. Hopefully you can see me and hear me. Let me know. Oh, that was cute. My upper TV, okay. I'm having tech issues today. We have, just for those who know, and we'll do this as a sound check really fast so I can see, you guys can tell me how my sound is faring. I'm on the west coast of the United States, and we are in the middle of a massive heat wave, record-breaking heat wave. We had power outages all day yesterday, and I ended up having my computer go down multiple times. And yeah, no red shirt, don't worry. I had my computer go down multiple times yesterday, so I am still trying to get things back up. And sadly, one of my casualties is my second computer, which I had working earlier today, and now it's not working. It's cratered on me. I had all of the live data products set up on the second computer, and I was going to switch screens, as you oftentimes see me do. I'm not going to be able to do that this time. We're going to have to pull up some stuff live on the screen that you see behind me. So it will be a little bit clunkier. I pray that things will load. I'm a little bit nervous that I won't be able to load data products because they won't show up if I'm streaming. You know how this stuff works. So anyway, you'll have to bear with me on this one. But it looks like at least you guys, yeah, not here in the Bay Area. You're lucky, Popcorn. You're you're lucky. It was 114 yesterday. By like 7 o'clock at night, it was still 111 or 107. I can't remember. I think by 8 o'clock it was about 107. It's been insane. Today's supposed to be a little bit better, but we'll see. But at any rate, I am a little bit compromised in my computer setup today, so I do apologize. Okay, audio was good. I'm glad. Thank you so much. UK had problems yesterday as well. Wow, Diana, I did not know that. Yeah, it's very... In Southern California, we oftentimes get last gasps in our summer, and around September, October, we usually get one more like final hurrah where it's a really bad heat wave. This is one for the record books, that's for sure. So, okay, good sound here. Sorry about the heat. Thanks, Karen. I appreciate it. All right, as I have all seen, I see Jerry saying all good, Dr. Scove. Thank you so much. As you have already seen, because I've been monitoring the chat even before we went live, both Mike and Jerry, who are the moderators, have mentioned, I think multiple times, that this is going to be a slightly different format than normal. And the reason for that is that I'm going to be querying you a lot more than I normally do. Typically in a mini course, what I do is I'll get through these big, massive sections, and then I will ask, pause for a Q&A for a little bit, and then we'll start another chapter, so to speak, and then pause again. This time we're going to be pausing a lot more frequently. So don't worry, for those of you who feel like you're being trampled and caged, don't worry. You're going to get a lot more chances to ask questions. It's just that if I don't get through, I want to be able to give you a sun to mud overview of data products, and I have a lot of slides to get through, which is always a danger for me, plus live web stuff. So we're going to limit questions as I go through data products, okay? And as a matter of fact, let me just jump ahead just so you know, okay, early on, for those who are, and I'll leave the chat up because you can see this still. But for those who are interested or are wondering, what we're going to do is do just a small subset of data products, literally from sun to mud, and I'm going to cover all of these areas. It's not going to be in depth. It's not going to be comprehensive. You're going to say, hey, my favorite data product is not in there. Right, it's probably not. And that's okay, because right now I'm just going to lay like the groundwork for what we're going to do in the rest of the series. In the rest of the set of courses, what we're going to do is we're going to go through each regime, okay, in detail. And we're going to pull out a lot more data products, and we're going to compare them, and we're going to talk about what is good, what is bad, and the proper and improper uses of these data products as we go through the series. But in order to do that well, I want to be able to first lay a foundation of all data products. And this structure, in case you're wondering, this wasn't just coming out of my brain. This was actually from a nice long office hours set I had with all the mini course tier patrons who wanted to come in and take a look and help me figure out how would be the best to present all this stuff. So this was the organization we came up with as being likely the best of all worlds, right? So those of you who want to get started and be able to go through from sun to mud and follow a space weather phenomena all the way to the end. They don't have to sit there through like 5 courses just to get to the ground. Okay, so that's kind of how we're going to be doing it. And because of that, every time I go through a data product or one of those regimes, I will stop and say, anybody have questions on this? And so it will be specifically on this. I don't want to be hearing questions about, gamma ray bursts when we're talking about KP. Okay, so that's what Jerry and Michael are talking about. They're trying to hold things, keep things a bit more controlled in that way, because otherwise I just won't be able to get through this whole course. All right, so hopefully that makes sense, everyone. We're not trying to throttle you or anything like that, just wanting to make sure that I can get through this so that everybody can enjoy themselves. Okay, let me quickly take off the chat here real fast. I'm definitely going to be struggling if I can't get... Oh, I wanted to use that computer so badly. Poop. Anyway, okay. And, oh, see, look, everything resets. You don't even see the same thing I see. I have to reset this. Power outages, don't you love them? I don't need these for that. Let's see. Slideshow, setup slideshow. Where is that? Setup show. I need to know. Browse by an individual. There we go. Now, hopefully you'll now see the same screen I do when I start. Yay! Okay. All right, so this is what we'll do. And like I said, you're going to have to bear with me because I'm down to one computer because of the power outages. And it's very frustrating. But I'll be better next time, I promise, as long as there's no heat waves. Okay, so to start this off, I have to say thank you to everybody in my Patreon family. As a matter of fact, I'm actually going to have to get a new set of a new page. I'm making people's names so small anymore if they don't fit on one page. But definitely thank you to my steering committee as well as my upper tier patrons. These are folks that are do one-on-ones with me and do are just really generous with their, not just their time, their expertise, but also with their with their funding this whole Patreon project. We have lots of good things that are coming to the fore, and I have to thank these folks for being part of that. Also, my mini course, my VIP, this is my steering committee, all of these folks, they are the ones who are steering the ship. And I don't know if I have any openings in my steering committee right at the moment. They might all the slots may be filled. And so you'll just have to hang out if you want to become part of the family, this very tight-knit family that really helps me decide where to go next, where to invest my time. Not even just simply in terms of what talks that I give, but also what courses I teach. Not many courses so much, but what I do at Millersville and who I get involved with and and just other cool things coming up. I don't want to let the cat out of the bag too quickly. So I have they're all my family. I appreciate them very, very much, and we get together more than once a month, actually, doing all sorts of things from heliobiology to super community work to working on very neat press kits and other long-term projects that we can talk about later that are going to benefit space weather and the community at large. And then on top of that, I've got the mini course patrons. Please, if you don't see your name up here, that's because I had a power outage and I couldn't update everything. Like I said, next time it will probably be 2 pages of this. Because you guys have just been so great, or so gracious and generous with coming on board and wanting to help fund these mini courses. You are the reason why these mini courses exist. You are also the reason why I do Friday, at least right now it's Friday at 11:30 my time, Pacific time, why I do the office hours. Right, and you guys know how to get a hold of me in those office hours. And any of you are welcome there. Okay, because this is where we decide how to do these mini courses. In fact, like I said, this Friday was how I figured out how to organize it, thanks to all of your input. So if you want to become a mini course patron and get some of those perks, please come on board. We want to hear your voice. I do listen to people. A lot of people are surprised at that, but no, I do listen. I really do. You guys are the ones that really guide me, because I'm here for you. I mean, why? I have other work that I do that's on my own, but here, for all of this stuff, I am here for you, and I want to be able to help you grow and take space weather to the next level, right? Because I'm not going to be around forever, and I can't do it, I can't do the world alone, right? We need a lot of people to be able to understand and forecast and help advocate for space weather savvy, right, in the world, and we just don't have enough of that yet. So thank you all. Okay, thanks, Jerry. I appreciate you putting up the link to the Patreon. If you want to learn more, please go there. Okay, I'm just scanning the chat really fast because I can see what you guys are saying. I just want to make sure. And thank you so much, patrons. Thanks, Steffi B. That's so sweet. Yeah, that's exactly my sentiment. All right, so overview of data products in all environment regimes. That is the name of the game today. Okay, again, it's not going to be a comprehensive, listing of data products because there are so many out there. And I probably should have put on here, it is the wild, wild west, because it is. The difference between space weather data products, and this is as an introduction, the difference between space weather data products and any other operational field that you've ever had the probably pleasure of dabbling in, is that space weather data products are funded for as long as they can be. Typically for the life, maybe for the life of a mission, of a spacecraft mission, which could be anywhere between 6 months to 5 or 10 years, possibly longer if it was a battleship, big, huge battleship mission. I shouldn't call it battleship because there's no war, but you know what I mean, a big monstrous thing. And some of those get extended missions, so they get lots of money. Flagship, that was the word I was looking for, flagship mission. Those missions like stereo, like SDO, we'll talk about some of these, today. Those missions oftentimes end up really getting funding to stay alive for sometimes decades, But it's not, yes, SOHO was another. But that's not always true for all space weather missions. And so data products come and go. And sadly, you have to be a bit agile in this field. If you rely too much on one data product, tomorrow it could be gone. Or they could lose funding, disappear for a while, and then come back. So understand that that's one of the biggest things about space weather. It doesn't have the money that, let's say, terrestrial weather does, right? At least not yet. I think a lot more eyes are turning in the direction of space weather, though, thanks to the May 10th event, and realizing that, wow, we've built in some sensitivities in our infrastructure because our sun was sleeping for 2 solar cycles, for 30 years almost. And that's a problem. That's a problem for us. So the small subset I'm going to go through today are the data products that are very robust. That's why I want to give them to you. That if for nothing else, if you're never able to go through another mini course again, you're going to have data products that likely will be around in 10 years. They may be modified, obviously, but they'll still be there for you, and they'll still function reasonably the same. And we will go through solar imagery and on-disk analysis, right, and coronagraphs. And now, again, the players may change a little bit, but they're going to be available to you and you'll recognize them. In interplanetary space, we're going to be talking mainly about models and real-time data from our upstream assets. Inside the near-Earth system, that's going to be inside the Earth's magnetic field, just inside, either in the pristine regime, where the magnetic field is nice, or even outside where it's kind of a bit messy. We'll talk about a few data products here. Then we'll jump to the ionosphere, right, where we get aurora, where we get radio propagation. And then we'll go to ground level, and we'll talk about things like geomagnetically induced currents. I won't talk too much about the ground level, and where we're going to start getting things kind of smeared out is when you talk about the ionosphere and the ground level, things get kind of touchy because some things that are talking about the ionosphere really are at the ground level and vice versa. So you'll see some overlap in places, and I may go back. But that's because the definitions are squishy, and you could place things, because certain things you look at, indices on the ground with magnetometers, really are reflecting what's going on upstairs. So where do you place it, ground level or upstairs? Anyway, so hopefully that makes a little sense. Okay? Yeah, you love Soho. I hear you. I hear you. I do too. I can't wait to have her be retired, though. The poor thing. It's been through so much. It's older than probably a lot of people in this room. All right, so we're going to talk about solar imagery, on-disk analysis, and chronographs first, okay? And again, I'll have to apologize. I was going to do switching back and forth from my charts to a live view, and now I'm going to have to pull up the live view. Crush fingers. I can pull up the live view easily. Okay, so obviously the first place I go to is NOAA's SWPC, right? And we call it SWPC, SWPC. It stands for the Space Weather Prediction Center, all right? And when I do a live view, I'll make the link look big. But you can even just Google NOAA, one word, SWPC, second word, and it will pull it up, right? Now this is the home page. I've broken it in half so you can see it slides down, you scan up, and you see these data products are the same as these. Okay. So what you have essentially on the SWPC homepage are 6 data sets. These didn't load properly during my screenshot, but I'll show them in a minute. These, just understand that even though this is probably the most reliable source for space weather data for the globe, there are a lot of other space agencies that even pull data from this place. This place is designed for the North American continent. Okay? If you are someone in Australia or New Zealand or Tasmania or even the UK, right, or India, right, take some of this stuff with a grain of salt, especially the stuff where you get into how space weather impacts Earth. All right? The reason for that, if you're not looking at a global model, if you're not looking at the globe, right, Space Weather Center, or Prediction Center, SWPC, as I will call it, focuses in on the North American continent. Okay? And so that can cause problems if you're taking everything for gospel. So that's the first thing. Now, will I show you other ones? Yes, actually, I had a few live that I had pulled up on the other screen, which I'll pull up again if I remember what oh yeah, I can actually turn this on, at least see what I had pulled up. So that's a good thing. Hold on. Oh, I can't believe that happened. Pardon me, I'm still mourning, as you can tell. This power outage has just killed me. It has just ruined me. All right. So we were going to go through, essentially, I think, yeah, we will go through all of the data products on this page. They are part of the essential package, okay? And we'll go through some more others. If you go to the Space Weather Prediction Center and you look at its products and data, this is really where it's a great place to go. You can go to dashboards, and that's fine, and they already have some prepackaged stuff, but I don't want you to rely on those dashboards because those dashboards, to be honest, don't always have the space weather data products that you really need. It's what SWPC thinks you need. That's great, that's fine, but it's not always the truth. Plus, we will stray from the Space Weather Prediction Center in some cases. I'm not going to be, this isn't just a homage to this particular repository. It's just that this repository is extremely robust, right? They are paid to do this, and so they will always be there. And so even though much of space weather data products are the wild, wild west, this is probably the most tame and the most reliable source of space weather products. Okay. So where we're going to go first, and I don't think I can zoom in, I have to go to a live feed here. Where we're going to go first is we're going to go into observations, but we're going to start looking at the solar imagery. Okay, so in observations, we're going to look at some solar imagery. I'll probably go to, I think I go to SUVI first, we'll see. Oh no, I go to the synoptic chart first. Do I really? I guess I do. Huh, wonder why I do that. Okay, not a problem. All right, so let me go here again, and then we'll pull up the synoptic chart in real life. Synoptic chart is right down here. I don't know if you can see that. Right down here, okay? And here's just a quick pop of, if you go to that page, what it looks like. I love this because I actually did this way back when. I made these charts a while ago. This is a snapshot of August, 12th of August of 2020. And look at this. This was, Sean Dahl did this particular thing. So this was right about solar minimum. Look what you see. It says weak mixed fields, hardly any spots. There's just teeny tiny something here, teeny tiny little prominences, just teeny tiny, right? Just not much going on. Look at the flare. This, and I'll read what all this stuff is. Here's, you can see 15, 1, 1, and 1, okay? What this means is, and we'll go into a real one in a second, but I'll show you here because you'll start laughing here in a second. C-class flares, you have a 15% probability of them happening. Why? Because of all of the active regions on the disk, and we'll talk about that more in a sec. M-class flares, 1%. Okay, so not going to happen. X-class flares, 1%. They never go to 0. Okay, this is essentially 0. Proton radiation storm, meaning particle radiation storm, 1%. Okay, so 15% chance for a C-class flare. Right. Most of the time I say where we are now, we're even below the seafloor. We're above the seafloor when it comes to X-ray flux. Here, they're just saying we're so low, we have 15% chance of even crossing that seafloor. Right. So this is a pretty dead disk. Okay. There is one active region that you can see here that's actually got a label on it. Here you can see an active region with this number. This is the active region number, but if it's in parentheses, it means it's no longer there. It means the submarine that's popped up to the surface is disappearing back down. Okay. Under here, you can see that you've got a little red mark. This shows an active region. Okay, so this is actually a sunspot that they can see on the disk. This was region 2770. And notice the split of numbers underneath. Notice they match the split of numbers here. I don't mean that they're the same numbers. I just mean that there are 4 boxes. 1, 2, 3, 4. Look, 1, 2, 3, 4. Okay. Those 4 boxes are telling you, in this case, 5% chance of a C-class flare, 1% chance of an M, 1% chance of an X, and 1% chance that it's going to give you a proton radiation storm. In other words, this little bugger is sleeping, right? Which is what we expected at solar minimum. You can see there was a nice polar coronal hole. How you can tell coronal holes is you can see this line that delineates the size of it, the edge of it, the boundary of it, and then you'll see these hash marks that point inward. Okay, doop, 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 doop. That's different than the dashed lines. Dash, 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 dash. I don't know why this is this thing? Why is it turning off? I think it reset. It turns off like every 5 minutes, even when it's plugged in. This power outage just reset everything. Okay. So the dashed line here, right, this is just indicating a neutral line where magnetic field directions on the disk, not associated with a coronal hole or anything, where they're changing. So where you go from a positive polarity to a negative polarity. See here, see the positive, positive, positive. That's just showing you that inside this region here, this is a coronal hole, and I'll talk about these numbers in a second. This is a coronal hole. This is outside the coronal hole. Then, and the polarity of the magnetic field in this region is positive, primarily. Then there is a meandering neutral line that then switches into kind of a negative polarity, as you can see here, but then it becomes kind of weak mixed. That's why he's calling it weak mixed fields. You can't really see any real neutral line location, whereas you can see it kind of one in here, likely a remnant of a sunspot region, likely, because typically sunspot regions, these submarines have polarity inversion, what we call inversion lines or neutral lines that separate one polarity, magnetic polarity, from another polarity. See positive, see negative, see the dashed line that separates them. You have that typically in and around sunspot regions. Okay, so they're looking at magnetic field imagery in order to understand this, right? That's what they're doing. As I've said in many cases in the past, I've talked about these sunspot regions as being submarines. So if you look at my Sunspots and Telescopes mini course way back when, you will see that I talk about these things that popping up through the surface. We talk a little bit about the solar dynamo. popping up through the surface, like periscope up. They become buoyant and they pop up to the surface so you can see the submarine sitting on the surface for a little while. They do their business, whatever that is, solar flares or just, in this case, just kind of languishing on the surface, not doing much. And then they disappear down. When they submerge again, oftentimes what's left is it's similar to, like, if anybody's ever gone whale watching and you watch the fluke of the whale and then it disappears under the surface, and then the surface gets this really pretty footprint, right? Very smooth, glassy water in a very well-defined pattern. Well, that's what you're seeing here. As these regions submerge, you get what's called a plage. And that's kind of like the whale watcher's footprint after the submarine or the whale dives back under the surface. Okay? And with those, you can see the nice boundary. So that's why Sean, in this case, was able to draw somewhat of a boundary. It was because there was still something left, because that footprint takes a while to dissipate. Down here, which is what we expect for solar minimum, right? There's been a lot of, especially in these areas, you don't see a lot of active regions. In fact, the ones at high latitudes, these were probably active regions appearing for solar cycle 25, because down at the equator is where the active regions were for solar cycle 24 as they were fading out, and there aren't any, right? Except maybe what's left over here. But these look like more high latitude ones. And you can see latitude ticks on the edge here. Now, that's just a cute little snapshot from when the sun was quiet. Here's one from yesterday. A little bit different, right? C-class flares, 99% for the whole disk. M-class flares with that 65% for the whole disk. X-class flares, 15% for the whole disk. Proton radiation storms or particle radiation storms, 10% for the whole disk. Lot different. Look at all the dashed lines. Look at how well you can define where the field direction changes. And you can see pluses, plus, plus, right? And you can see minuses, minus, minus. These are all neutral lines, and they can scatter all around the disk. During solar maximum, the magnetic polarities change so much. This is what I call a lava lamp, because it's very clear that stuff's just everywhere. Where'd the polar coronal hole go? Gone. What are coronal holes looking like right now? This is a coronal hole right now. This is a coronal hole right now. They are scattered all over the place, okay? Here in the next couple years, you're going to see them grow and become more finger-like, much, much larger, okay? But during solar maximum, this is what they look like. They completely disappear from the poles, and they become these other they disappear from the poles, both the north and the south, and they become these other structures that are at mid-latitudes or just kind of all over the place. I mean, it's crazy where they are. Notice all the active, or all the sunspot regions now. Okay, see them all? Now, so the Space Weather Prediction Center, whoever the forecaster is, they put their name up there. And in this case, who is it? Patterson. They put their name up there, so you always know who it is, right? And they do them, I think, about twice a day. And they write the time that they do them. They also write the time, or write exactly the time, that they looked at these different images to then create this composite that they draw themselves. Okay, so they look at H-alpha imagery. They also look at sunspot imagery, so white light. They look for coronal holes, probably 211 angstroms, or 193, which is, for those who don't recall, it's the pink sun, which is 211, or 193, which is the bronze sun. And then they look at the magnetogram, the HMI data. Okay. And these are the times that they looked at to be able to draw this. So if they ever had to go back and figure out why they did what they did, they've got the reference images that got them to draw what they drew. Okay. The west limb was at 260.75 degrees longitude at that time. The east limb was 80.75 degrees longitude at that time. There's a fixed longitude coordinate system on the sun, and as the sun rotates, those longitudes stay fixed, and so that's why these change. Okay. Because what you can see from Earth is only a part of the sun. People wonder why I use the solar disk. This is why. Because you're never looking at the whole sun. You don't see the whole sun. You see a part of the sun. That part of the sun looks like a flat disk. Okay, you're not even seeing, and remember, you have projection effects because the top of the disk is like my hand. You're not seeing this. You're not seeing this. You're seeing this, right? Down here, you're seeing the flat of my hand. Out here, you're seeing this. People forget that. And so all we do is we project all of this stuff flat. Okay? But those are projection effects that cause major problems. Not so much at where this hand is, because you're already seeing the flat of my hand. But down at the poles, and as you get into higher latitudes, you have to flatten that out, and you're not going to be able to see the stuff that's out here nearly as well. So we call this a disk because it's the flat disk that we see, right? But there are projection effects in here that you have to be aware of, which is what makes it difficult to forecast whether solar storms are going to hit Earth when you start getting to the edges, what we call of the Earth strike zone, because they're so far like this. Anyway, getting back to the sunspot numbers, you can see them here, right? And this is where you will find new sunspot numbers officially numbered for the globe. You will find them in these diagrams. Where's one? Here's one. Here's one. Okay. Look at the numbers underneath. So for region 3806, what is it? 55? Is that 10? I need to really zoom in to find this out. 55, 10, 1 and 1. Here's 25, 5. Looks like maybe 1 and 5, 1 and 1. I'll zoom in. I'll get to the real live one because this was yesterday, and I'll be able to zoom in on the live one. So hopefully this is beginning to give you a better idea of what we're looking at. Now, am I going to go through everything on this page? No, because again, I could get lost in the minutia. We can do that when we do the deep dive. Okay. Next region number. Notice 3817. It's telling you which one's coming next. So when they do a new one, this is what it will be. Carrington rotation. So they're telling you the days of the Carrington that, yeah, let me be careful with that. They're telling you what part of the sun is returning. And I'll have to go look to see what exactly numbers that they're talking about here. But I'll do that in the deep dive, okay? I'm trying to think if there's anything else that's super important. Oh, right, one other thing. So I was talking about the numbers of these coronal holes. The plus number, well, let me start with the top. The top number is the number of the coronal hole. They number them just like they number sunspot regions. So that's the number for the coronal hole. The plus or minus is indicating the polarity either toward or away. Okay, and we can talk more about what that means. Certain times of the year near the equinoxes, you will get certain polarities, whether it's a positive or a negative polarity, that will then be more what we call geoaffective. Okay, depending upon the polarity, depending upon the month, the season we're in. We have the Russell-McFerrin effect kick in. Okay. And then okay. I was getting confused there. I'm like 13, that doesn't make sense. You have a 1 here, a plus here, then you have a slash, and then you have a 3. Okay. That is a quality flag, letting them know how much, and I think that information is in the site below it. I'll show you where that information is. It's a quality flag saying how well formed that hole is, or what their confidence level is that they've got the boundaries and everything correct. And we'll talk more about that. But the easy way to recognize with a coronal hole, if you're at summer, like straight summer near the solstices, don't worry about it. These don't really mean much when it comes to the polarity of the holes. But if you're at the equinoxes, they do. And the easy way to remember is the acronym SNAP: spring, negative, autumn, positive. So if you're in the spring and you see a negative coronal hole, a negative polarity, that coronal hole will be more geoaffective, meaning it'll cause a bigger storm. If you're in the autumn, okay, near the autumn equinox in fall, then a positive coronal hole like this one will be more geoaffective. Of course, the size of the hole matters. We may not get any wind from this any fast wind from these coronal holes because it's so tiny right now. But if this were a bigger coronal hole, I would say, yeah, we're getting closer to autumn. We're in autumn, so we're closer to the autumn equinox, And this one will be more geoeffective because it's got positive polarity. Make sense, hopefully? So that's kind of, in a nutshell, what those things mean. Certain people will do, and is this one I got a movie? This may play really quickly, but this, well, I guess just maybe a little bit. I wish it would play, wish it would loop. But it reset everything, so my loops don't loop. Okay, so as you can see, different players, different forecasters do different diagrams. But here's a perfect example of one moving on. And if I can stop it, let me go back here. Spencer, I love Spencer. He's teaching everybody to, this is Terry, he's teaching everybody to do them digitally. Isn't that cool? So now coronal holes, you can really pick them out because he just makes them black. Isn't that neat? And the dashed lines are much, much clearer to understand. I really love Spencer's work. So Terry, keep at it. Keep getting these people to do them digitally. They're really awesome that way. Although, you know, you may be a little nostalgic for, you know, for hand-drawn ones. Either way. Okay, let's see now. Let's see if I want to, yeah, okay. Let me go. This is where I have to, sadly, pull this stuff up on the different website. Okay. Hopefully it'll reload. We'll see how quickly. All right, so it's reloading. So that helps. Now, whoops, it didn't, sadly, it didn't reload. It didn't make the link bigger. I was hoping it would size all this up, but hopefully you can see it. It's swpc.noaa.gov. Okay, that's how you get to this site. And in here, what we'll talk about first, products and data. And this I can zoom in, so I will. Boom, go down to observations. There's the solar synoptic map. Click it and we'll see the one for today. Okay, so there you go. It doesn't look all that different than what we just looked at. Now this is WC. No, not water closet. Nice try. I have no idea who WC is, but I hope they will put their name out there so I can say hi to them. But as you can see, very, wow, tiny writing, good Lord. And very detailed. Look at this. This person is awesome. They're actually drawing the umbra and the penumbra. They're drawing the teeny tiny spots, right? And they're even drawing arrows. Wow, I don't see this very often. This is a real treat. So keep doing it. This is cool. So you get to see exactly what they're numbering and why. So 3815, 3813, 3816, you can see them all. They take time to draw the numbers. These here are filaments, small filaments. Sometimes you will see long ones like worms, and they're typically drawn like this with complete full hash, okay? And they always, well, most of the time, land on neutral lines. And even the ones that you can't see like this is a filament. It doesn't look like it's on a neutral line, but likely it is, because that's just how they work, right? It's the kind of physics that occurs, how you create. Whether you get a big solar storm being launched, you know, big coronal mass ejection being launched right from an active region, or it's a filament, a lot of the same processes occur, and there's going to be a neutral line in there, typically aligned along the axis of the structure. But then, of course, in interplanetary space, these structures do all sorts of crazy things that then make it very difficult to predict how they're going to hit Earth. But as you see here, 60, 20, 5, 5, right? So you, just by looking at this, not even looking at imagery, you can get quite a bit of information. This one has a pretty good chance for M-class flares, a small chance for X-class flares, and pretty active. But this one right next to it, 90% chance of C-class flares, 25% chance of M-class flares. That's at R1 to R2 level radio blackout. This is the more active part of it, right? And good old WC actually labeled exactly where they're looking, which was kind of nice. 3814, let's take a close look at this. So see, do you see how I'm using this? Get that stupid thing off there. Okay. You really get, even without looking at any imagery, let's say you don't have time. Let's say the imagery isn't loading, right? And someone asks you a question about space weather, you really needed to know whether or not something's going on. You can tell immediately where you're supposed to look by just looking at some of this stuff, right? And granted, these things only are done maybe twice a day, so could a new player emerge and really start firing flares at that time? Yes. Does that happen? Yes. It's not perfect. But it gives you a nice summary where you don't have to go reinvent the wheel. And so I strongly advocate people using these because they really do help you. And they're really nice for confirmation. Because if you're like, okay, I think this one's going to go, or I think this one's a big one, go take a look at what SWPC thinks, right? Because this is what these guys do. They're trained for this. And they'll lay it out, right? Here's a sunspot region that died, that submerged, it's back under the water again, right? How do we know? It's in brackets. This sunspot number is no longer, it's being tracked, but it's no longer an official sunspot. And if you were to look in the white light imagery, you'd see a plage. You wouldn't probably even see a sunspot. Some people ask me, well, how long does it take SWPC to number a sunspot? Oftentimes about 24 hours. They'll follow a little spot on the disk, because sometimes they emerge and then they go, nah, I'm not feeling it, and they go back under the water. So, SWPC's not going to waste a sunspot number on that. So they'll wait. Sometimes a sunspot will emerge here near the edge of the disk, and they won't number it. Why? Because within 24 hours it'll be out of view. Don't bother. So they don't. They'll show new, they'll write new, but they won't necessarily give it an official number. As you can see, a lot of these sunspots are very, very complicated, right? And we'll talk a bit more about how to take a look at those in a sec. But this is the current sunspot. Is that as far as it goes? Okay. This is the current sunspot diagram, synoptic chart. Okay, and like I said, they do them multiple times a day, and it looks a lot different in solar max compared to solar minimum. Okay, now hopefully that helps. Let's see. I wonder if I can get both of these up at the same time. Okay, so the next thing we're going to look at, and I won't pause on that yet, because I want to talk about sunspot numbering systems. So we'll talk about, I'll keep going until I get through the end of this. Okay, next thing we're going to talk about is SUVI. Okay, now SUVI imagery is a lot like SDO. As a matter of fact, Lockheed Martin, the same team, built the two instruments. SUVI is kind of a downscaled version of SDO's AIA imagery, the atmospheric imaging assembler, atmospheric imaging assembly. That's AIA on SDO. That's where we get all the pretty colored pictures. There are some differences, though. SUVI has a wider field of view. That's number one. SUVI has a faster cadence. That's number two. But to get all that, SUVI also has a lower resolution. So images that look sharp in SDO look fuzzy in SUVI. Okay? But that's space weather. They care more about the quickness. They care more about a wide-angle field of view. They don't care so much about the scientific details. So that's the difference between operations and science. Now, and academia. Now, notice this again is an older version. This is back from 2020. Okay. Where are the sunspots? Do you guys remember solar minimum? Look at it. Man, it looks like a fuzzy lion. You know, I mean, it looks like a plushie or something. It hardly looks like a sun that I recognize. It's just this cute fuzzy peach sitting here. But let's look at it today. Let's go to products again. I'll go down to observations again. Whoops. Yeah, I'll stay on this side. Observations again. And where are you? SUVI. Okay. SUVI. I'm so glad it's loading. Yay. Look at the difference. Right? What a difference a day makes. So no longer fuzzy peach. We've got all sorts of fun stuff happening. You can actually still see the two bands of active regions, right? One in the north, one in the south, that are slowly kind of crushing down. So you can tell we're not completely starting the new cycle. We're definitely in the middle of it. One of my favorite imageries to look at is 193. It's a really great overview. And again, I think Sunspots and Telescopes talk about this, that particular mini course. So I'm not going to go through the details of everything. The neat thing about SUVI is that you can get the last couple hours at pretty high res just right there, right up top. So if there's a flare that's popping off, you know, in the last half an hour, you will see it with just this short little thing. You can actually see what little activity is going on right at the moment. Too bad we don't have something really cool going on. That'd be fun to see right now. But we do have lots of filaments that we're worried about right here. Now, if I go to a different wavelength, you'll be able to see other things, right? Here you can see filaments much better with a lot less interference from parts of the corona. So you can see where some of the things that, a bit more activity. You see prominences much better, right? But this is the same kind. These are the same wavelengths. This is 304 angstroms. The one I just showed you was 193. Same color sun as SDO AIA. As a matter of fact, I think all of the wavelengths they show are of similar color as SDO. 131, 94, they all are, yeah. So the cyan sun, if you were to look at that, will tell you where solar flares are occurring. You'll see them as paparazzi bulbs. Right, I'm not going to go into the details of that, but that's what's nice. If you click on this, it'll be bigger, so you'll see more activity. There's a little flare there that we didn't even know on the other one. You can see it right there. Yeah, I'll move my cursor out of the way. There you go. So you wouldn't have seen that on the other one. So it's useful to know what the different colors do for you, but that's not this course. That has been a previous mini course. Again, it might be sunspots and telescopes, probably CMEs. The C series will do it for you as well. But I can put in some links to things later if you guys want. All right, so this is where you get this imagery. This is the easy way to look and compare with the synoptic chart. Another place to go to get the imagery, I think I'll be showing that next here. Let me see. Let me go to the next slide. Yes, SDO. Okay, which I'll show in a second. Once again, this is during solar minimum, so this is the bronze sun in solar minimum. This is the 193. We'll talk about what it looks like today. And to go there, an easy way to do it in a Google search engine, so you don't have to have links to everything, you type in SDO, AIA, and then GSFC, Goddard. Okay, and it'll just pop up. So you want to see SDO, meaning the spacecraft, AIA, meaning the imagery, and then Goddard Space Flight Center. Gov just popped up automatically, but you don't need it. And what it will do is give you the very first link, I guarantee you. If it doesn't, there's something terribly wrong. Okay. And there we go. Here's a new version of... Look how different 171 looks. And yes, it ramps through all the imagery. Okay. Now, what's cool about here is that if you notice, just even by looking at the images, what's cool about this imagery is that not only do you get more colors, because this is the scientific grade instrument, not only do you get more colors, you also get higher resolution in terms of spatial resolution. Okay. There are several different ways of doing data. If you go to the data tab, there's several different ways of doing it. You can go to the sun now, which will give you nice imagery, nice like pictures. But you can also go to the browse data and you can actually create movies. Okay, and I don't know if it will let me do this, but I'll try to see if I can create one for today. You put in day in, then day to start, day finish, and then whatever color you want. Let's do 211 for fun giggles. Browser data, okay, unless you want to download stuff. Sometimes this function doesn't work very well. Resolution, you can do 512 or 1024. Obviously 1024 by 1024 is going to be bigger. And then this just simply means, do you want every image in for the display here? I think that every image, consecutive images they give you is like every 15 minutes. It's just by default. But if you want to skip and make it like once every half an hour or once an hour or something, then you skip an image. So if I wanted only once every half an hour, then I put 2 here. If I want once every, several hours, I'd put 4. So you can skip every image or every other image or something like that, and it will do that for you. Okay, I'm going to put every image if you want the highest resolution, or highest cadence, which, like I said, is, and we'll see if it loads. It may not. I may have to go to like 510. Oh, there we go. Hey, it's being good to me today. Oh, look, something we did not see very easily in the other wavelengths. We see pretty well here. I was wondering. I was looking at 335 and going, boy, that actually looked like their CME just launched. Yeah, I paused for a second when I saw that image and went, should I say anything? No, I won't right now. we have something interesting happening. Now, why did I not see this in 304 and 193 in SUVI? I don't know. I should go back and check. Maybe because it happened too long ago and it's already after the last few hours. Let's see, when did it happen? Yeah, 7. So it was at 7. We're seeing something that happened. SUVI only gives you the last couple hours. So this is a perfect example of why don't just trust SUVI in the last couple hours if you haven't checked for a while. Unless you're checking all the time, SUVI's only going to give you the last couple hours. This is giving you an entire day. So do we have a CME coming at Earth? It's really on that hairy edge of the Earth strike zone. But hey, here's some space weather forecasting for you. We'll see. I have to take a look at coronagraphs, and maybe we have a good chance because this happened at 600 UTC. You can see right around here, 6 to 7. It's where you see that breaking off. And again, this isn't a CME class, so I'm not going to go into all the details of what I see and why I know the CME launched. Right? So we have a solar storm coming, and it's going south, mainly south, slightly east of Earth. But it is at the hairy edge of the Earth strike zone. Now we'll go to coronagraphs and we'll look for something around, 7, 8 UTC coming off the south part of the limb, and we'll see if there's enough of a partial halo to indicate that this thing may be coming at us. But this is good. So pretty soon, SWPC will have a model that will likely show this one because it's close enough. SWPC doesn't always model things that are coming to Earth because that are not going to come to Earth because they only care about Earth. It's NASA that cares about the assets everywhere. So NASA will definitely model this probably several times. First for the shock, and then second for if this has a shock. This is kind of gentle. Let's let it play. Maybe weak shock, maybe. It's going to have a little bit of competition with some little pop here. Pop right there. So there may be a little bit of something in the background. Sorry, I'm doing just a little bit of space weather forecasting for you guys right now. Just trying to look at the rest of the disk to see if there's anything else that we're going to see in the coronagraphs that could compete with this thing and mask it, camouflage it. But I don't know. Anyway, notice how highly detailed everything is. That's the big difference with SDO and SUVI. Okay, with SDO, AIA, and SUVI. All right, but this is a really good tool to use. Another cool thing to use from the SDO is, let's see where they show it. There we go. Browse data dashboard. See this? You can actually set this, and I do this all the time. Hopefully, it probably won't load very well here because I'm asking it to do a lot. Okay, it's only got 3. So in this case, it's just giving me 3 images or 3 movies. These are at 512 pixels, so they're small movies. But what's cool is that you can actually go up to, if you see this dashboard here, this link, you can press this link here because it's not showing me there. You can copy this. This is the link for what they call the current configuration. So if you copy that, which I will, and I then put it, let me just open a new page with that in there. Boom. The reason why I'm doing that, and I'm giving this one, is now you can see in this link, if you can see it, it shows the colors. It's saying query, and then it says 193, 171, and HIM or HMIBC. What if I wanted to add, I don't know, let's see, 0131. Haha, now I got another sun. This is what's cool, is that you can actually set up the link by just calling out the angstroms of the views you want in the order you want, and then save that link and click on it, and it will bring up the latest movies for all of those all on the same page. So it's really nice because this way you get kind of a neat little view of the sun in whatever wavelengths are your desire, and you can get HMI imagery, right? This is the magnetic imagery that we use to designate what sunspot classifications are. Okay, so that's a neat one about the SDO dashboard. Okay, and now there's more stuff, but I'm not going to go through it because takes too much time. But this should get you started, right? Because this is, again, just the fundamentals. So again, you got SUVI, which will show you just the last couple hours, right? In the same color, so this is 131 angstroms. And then you've got SDO, right, which even in the dashboard, look, 131 angstroms, same color. Okay, so 131 angstroms is going to be green, the bluish green, the cyan color. 171 is going to be gold, even in SUVI, as well as AIA. 193 angstroms is going to be bronze. Okay, you're going to see that. The only thing is that, for instance, if I wanted 211, is it a comma or no colon? Okay, 0211. Pop. Uh-oh, I messed up. Oh, it put no, I don't want a space in there. That's not what I'm asking. What are you doing to me? There it is. This color is not in SUVI, okay? This is only AIA. So if you go back to SUVI really fast, you can see its colors, but you're not going to find 211. What you will find is this thing. I don't like this thing. You guys can play with this if you want. It's supposed to be a tool that tells you where things are, but a bright region. This is just a smear. I'm not really sure what this is supposed to help you find. The coronal streamer belt, maybe? And where there's a flare, is this always right? Where there's filaments, is this where all the filaments were? No, there were lots of filaments in here. If you look at the synoptic chart, you'll see filaments in lots of places. These aren't the only ones. Matter of fact, there's a ton of big ones down in here, but it's all overlaid with this bright region stuff. So this is fun. It's a fun toy, but would I put any stock in it? Heck no. I would use the synoptic charts over this any day, okay? It's a cute AI toy, but outside of that, no. Don't trust it. Okay, let's see. Now let me go back to this. Okay, so HMI observations are powerful flare predictors. And so this is what we're going to get into next, because I want to talk a bit about how to, I actually had a patron who asked, how do we do the flare classifications? Well, this will be something that we will do a deep dive in when we go into the solar imagery stuff, because it's just so intense. Because there's so many different ways of classifying these sunspot regions. And I will only show you the Mount Wilson version because that is what is the most common. You see it in the most common in most common websites. People talk about, this is where you see alpha, beta, gamma, and delta, that type of thing. It's also used in the very popular and very cool Space Weather Live website, which I strongly advise you to go see, and we will pull it up here shortly when I start talking about this. But I will pause for a moment to ask if anybody has any questions about the synoptic chart before we go into this. Questions about the synoptic charts or the imagery in SDO. Okay? No smoking in class. The first thing I look up when I see that. Thanks, Lara. That's classic. You can smoke, just outside, right? Just kidding. Okay. Awesome, Nick. I see that all new tools have to start somewhere. Coronal hole numbering, who and why. You know what? I'd have to go dig that up. I think the coronal holes are started at the beginning of the cycle. And who numbers them? Likely SWPC. I think they can have control of them. But they're the same. It's the same kind of thing as sunspot numbers. But I do think they start over for each solar cycle. Now I have to verify that, but I do believe that's the case. So we were, what was the sunspot number we were at? Was it 35 or 65 or something like that? And the interesting thing about coronal holes is that depending upon what imagery you're looking at, the coronal hole will look either larger or smaller. So I will need to brush up and find out if they're always looking at 193 angstroms for this, or if they look at 211, or what are the details. That does remind me, I forgot to mention to you, thank you for reminding me there about that, Brian. If you go to the solar synoptic map, right, it will show you, if you go down here, down at the bottom, usage, impacts, details, history, data. Okay. I believe in the details you will see reasonable definitions of how they look at these things and how they define and how they what the nomenclature is, what the what the imagery, what it looks like, what the delineations look like. Okay, so it says a neutral line boundary at different magnetic polarities. For neutral lines, coronal holes have a single polarity magnetic regions. Let's see, where does it say? The boundaries, there we go, I'm looking for that. The boundaries of the coronal holes are shown on the synoptic drawings as lines with hash marks on the coronal hole side of the boundary line. So in other words, the hash marks always point into the coronal hole. If you're Spencer, if you're Terry, you just darken the whole coronal hole, and then you have the text the opposite color, so you don't have to do the hash lines because it's clear where the coronal hole is, right? So there are some forecasters that deviate from this a little bit because they can, but it's unambiguous. With Terry's stuff, you know where the coronal holes are, right? Because they're all black. Anyway, so there's stuff here. There's also explanations of the coordinate systems that they're using, right, and what these things mean, what the ranges mean. The group labeling, spot groups, where I was already talking about the 4 boxes, and then coronal hole labeling. Here was the thing that I wanted to look at. So beside the figure is a number from 1 to 4, representing the confidence of the coronal hole analysis. Okay, so we saw a coronal hole with analysis of 3, and I kind of balked and I said, yeah, that's it wasn't a 13, it was a plus with a hash trying to separate the 2 categories, and then a 3. 3 meant that you were reasonably good, right? 3, fair. Okay, they're less good than that, fair. And that's because right now, near solar maximum, coronal holes are kind of hard to define. They're really tiny, number one, and there can be a big distinction or big difference between what they look like in 193 and what they look like in 211. 211 will almost always have them bigger. And if you were to go back in time and look at Yoko imagery from ages ago, and you look at SXT or even HXT, but SXT in particular, you will see coronal holes that just are massive. And it's because in X-ray, the coronal hole boundaries look even bigger. There's anywhere near coronal holes, they just don't have an emission in X-ray. So that's one thing I wanted to explain to make sure that you guys had that too. It's not just this course, you can get a bit of this. But hopefully the course, by me talking specifically about these things, you're able to then piece it together, and then you can use the details down below as a reminder of what we talked about here, okay, what we went over. Okay, so hopefully that answered that question. Best explanation, thanks. Excellent. So happy. How much of your content do you cover in these versus if one joined Millersville University program? Yeah, that's a little bit off topic at the moment, but I will answer it. In Millersville, you get a more comprehensive understanding, and you get behind-the-scenes stuff that I will not talk about in public, and there's lots of reasons for that. Which I will not go into here now. People have taught, I've mentioned why in the past, but I don't want to get too far off topic. But yes, you get a different sense of things. I spend more time here, oftentimes getting lost in the details and answering questions. Millersville is much more focused, but you also get topics that I do not talk about here. And you get a better sense of how to enter the field in terms of the types of things you're going to encounter, the types of people, the types of relationships, the types of problems that we come across. And so it helps you navigate the work environment a lot better. Plus, there are other topics, there are other subject matter that I go into in more detail. Yeah. So they're different. They're different. They're both beneficial, but they're different. I've had some of my SWN people go and take, like when we talk about Carrington class events, for example, they've gone off and actually watched the Carrington class event mini series, the mini course series that I did, because I don't have time to go into all of that in the SWN program. So some of the advanced topics in particular, well, I don't want to say that, not advanced topics, because all the advanced topics are in there. It's just that I have time to give more examples in these mini courses, okay? But again, there are some topics that I don't talk about here in mini courses that I do talk about in SWN. So that'd be a good conversation to have maybe offline with me. Okay, so did we get all the questions? No, I don't think so right now. I'm not sure what's on the far side right now, but I haven't heard any NASA folks screaming about big solar flares. So I'm not sure we have anything Carrington worthy on the sun's far side right now. I think the sun is taking a slight break. Okay. So let me go back to this part. Okay. So the neat thing about HMI data, right, and we just looked at HMI data from SDO. You're not going to see this in SUVI. Okay, this is only for SDO, not in this case, not even AIA. HMI is a magnetic imager, heliospheric magnetic imager, and it will give us information about the magnetic field coming in or going out and coming into the plane of the disk. Okay. As you can see, they all pick up all of the sunspot regions, but if you were to overlay them, which we'll do that in a sec, overlay them, they don't always lay right on top of each other. And part of that is the imager, part of that is also just the nature of what we're looking at. But the magnetic information in here gives you a lot more information than just looking at the white light sunspots. Okay? So for instance, because of the magnetic imaging, we recognize that region, 3806? 3806 is this region here. This is more complicated and far more, not far more, but a bit more of a flare player than this region down here, 3815. 3813 and 3815. This is a gamma, is it just a gamma, beta gamma configuration, I think, and this has some delta spots. Yeah, we can see some of the excursions in here coming into the penumbra of others. Well, we'll talk about that in a sec. Okay, so you can't tell that stuff from just looking at the white light images. Well, let me take that back. Yes, you can. It's just harder. You can tell, but you don't get magnetic polarity, and so you don't really have a good feel for what's going on. Here, the magnetic polarity is dictated or is indicated by the color. If you have blue and green, and oh boy, I'm always going to get this backwards. Blue and green, I believe, is coming out. Red and yellow, orange is going in. I hope I got that right. Okay, so this is away, this is towards. Now, sunspot classification systems, the only one I'm going to go over in any detail whatsoever is the Mount Wilson, also known as the Hale classification system. This is the one that is most common, okay? And it's also the easiest to understand, okay? There are others, but we're not going to talk about them today. This one also is on Space Weather Live, which is to me, one of the best sites in terms of looking at the details of sunspots. You know, obviously using Space Weather Prediction Center for the synoptic charts, that's awesome. But if you want even more detail, Space Weather Live is amazing at doing this. Another good one is SolarHam. If you guys use Kevin's site, that's a pretty good one too. But Space Weather Live is a bit more intense. Plus, it's got an archive of these things that are much easier to access. It's just a bit more powerful. Okay. Going over them quickly, again, we will do deeper dives later in later courses. The unipolar, if you have just a single sunspot, right, you have what's called an umbra. That's the darkest part, and then a penumbra. I've talked about these before in prior courses. The easiest way to get an analogy in your head is if you've ever seen a submarine under the water that it pierces the surface of the water and you're looking at it from like an aerial view. You look down, the part of the submarine that is surfaced and that has broken the surface of the water is the blackest part the darkest part. I mean, it's solid, right? And then the part that's under the water you can still see the shadow kind of under the water, but you also see the water. So it's like kind of faded into the distance, and you kind of see a little bit of the blue water over it. Okay, so it's not quite as black. Now, the part where the submarine pokes out of the water, the blackest part, that's the umbra. The part of the submarine that is still beneath the water, that's the penumbra. Okay, you can see the difference. It looks very, the region around the blackest part, around the umbra, does look like there's something there, but it's literally the same kind of phenomena. You've got some of this boiling light water, as I call it, as I've called it many times in the past, kind of oozing over the top of this sunspot to some degree, because it's still able to penetrate into a little bit, and it lights up that region a little bit. So the penumbra is darker than the surrounding region, which has got free-flowing light coming up from the inside. It's inhibited in this region, but not blocked. Here, it's blocked, okay, completely. So when you have a single sunspot, umbra and penumbra show, and we call that an alpha. It's an alpha classification. If you have two of them, and magnetically they're going to be opposite polarities, so one will be red and orange, the other will be blue and green. Okay, when you look at an HMI imagery, that will be a beta. And yeah, you might have some little satellite spots, but you're going to mainly have this kind of thing, and they're not necessarily interacting. Okay, you can also have delta if you get. Now here's a clean neutral line going between the two, and you can actually see in magnetic. In the magnetic situation, magnetic imagery, you can actually see where the change in polarity occurs. We'll talk about that here in a sec, okay? Because we'll talk about the magnetic polarity in a sec. So now you've got small sunspots, that have the same polarity on one side and the same polarity on the other, but then you've got the neutral line in the middle, okay? And that's the beta, where they're really clearly delineated. When the neutral line is a bit messy and you've got sunspots of one polarity over on the sunspot of another, either in the penumbra or kind of close to it, that's when you have a delta configuration, where you begin to get magnetic mixing. When you get to a delta, that might be showing a little bit of activity, okay? When you get to a gamma, now you're having complicated neutral line, right? There's a little bit of complication. You have multiple neutral lines in this sense. Now you're having a very complex neutral line. You have multiple spots that have umbras and penumbras. Okay? It's becoming like an armada of submarines piercing the surface. That's when you get to a gamma. And with a gamma delta, that's when you actually have polarity inversions, where you have the polarity of one magnetic polarity entering into the penumbra of another magnetic polarity. So you're getting lots of really, serious magnetic mixing. You're getting lots of really strong magnetic field of opposite polarities coming in within really close range. Okay, these are typically called delta spots. And when that happens, here's delta spots, where you have, again, magnetic polarity, the wrong magnetic polarity pulling in. I think that's what they're trying to show here. There's a neutral line. Can you see that neutral line going right through here? So these are magnetic polarity of one kind, and that's the magnetic polarity of another kind. Those are the umbras, and penumbra is circling around. So you have then these intruders literally intruding in on the penumbra of this guy. That's delta. This X-class flares, big X-class flares. If I saw this configuration, I'd be like, holy crap. I'd be like, this could give you anywhere between an X2 and an X10, possibly higher, if you see this type of configuration. Now, does that mean that every gamma delta configuration is going to do that? No, not at all. But there are some that are pretty intense. Okay. As a matter of fact, I think we have gamma deltas right now. We'll talk about that in Space Weather Live. So this is what's cool about this particular plot, this particular sketch, and I wish I had the accreditation. I gotta go find who did this. I had this in my list of things. I'm like, oh, I have to show this, but I don't have. I can't give credit to whoever did this. But I thought it was really smart. You have white light, that's what this is. You have magnetic. Okay, so this is HMI. This is what it looks like in magnetic imagery. This is what it looks like in white light. Okay, obviously it's idealized, but it gives you an idea. So an alpha configuration, right? That's just one spot. It's all same polarity, so magnetic polarity is just going to show you one color. Okay, in this case, we're just doing black and white. Okay, but there's the umbra and penumbra. Okay, beta, well, you're going to have two of them, two main clusters or two main spots. In this case, they're showing slight, you can have a single spot. Here they have two, but it's all one penumbra. And they're going to have opposite polarities, right? If you look at the HMI imagery. Okay, that's beta. They don't really interact. They're very clearly delineated. Okay, you get a beta gamma when things get more complicated. You can have those same delta spot, same beta configuration, but now the magnetic field, you've got other spots, you've got a neutral line that's changing, and you've got more than one neutral line. So you have to have a neutral line here, you have to have a neutral line here, and you have to have a neutral line here between, because you keep flipping polarities. So that's where the gamma comes in, is when the neutral line is no longer simple. It becomes more complicated. Now beta gamma, as you're seeing here, you've got neutral lines that are surrounding, as you see, surrounding this situation. It's getting even more complicated. Okay, and that's, as far as I'm going to take it right now, there's more specifics about it, but just let's say a beta gamma can get to a point where they begin to start delineating other things. Okay. Now, a gamma by itself, you don't have any penumbras, any big penumbras. You just got little spots, but they've got magnetic polarities that are kind of all over the place. So lots of little neutral lines. Hopefully you're getting to realize that what gamma means is having multiple neutral lines. Okay. Now, how do I want to explain this? Okay, so if we go back to the beta, we're going to start talking about now a beta delta. We have just the beta, just as we had before, but in this case, you actually have a small sunspot inside. So in other words, this small sunspot here, right? We talked about how betas can be very simple. They can have just a single sunspot, or they can have multiple sunspots inside a single penumbra, but they're all the same polarity. So that's why it would all be white. In this case, you have two sunspots in that same penumbra, but one of the sunspots has an opposite polarity. In white light, they look the same. Magnetically, not a chance. This is a much more dangerous sunspot cluster than this one. This one won't fire any flares. This one could, very easily. Okay, beta delta. So this is why you need magnetic imagery to be able to tell where the bad actors are, because it's always about magnetic fields of different polarities coming close to one another. Okay, that dictates everything. Everything in magnetic field, or everything in space weather, is magnetic fields. Always pay attention to that. Magnetic fields tell you a lot about what the electric fields are doing. And yes, you can look at the electric fields, but electric fields are much more complicated. They move much more quickly. They oftentimes can be very stochastic, where the magnetic fields will be a bit more ordered. And you can make much more easy sense of them. But they're right hand and left hand. Okay, they shake each other's hand. They work in concert. So why not look at the ones that are a bit easier, a bit more well-maintained, well-controlled? It's like the difference between looking at a jump rope that's held at both ends while people are swinging it, and a jump rope that's only held at one end, and people are just swinging wildly. A wild one is just all over the place. You don't know where the heck it's going to be. You can walk up next to a jump rope that's held at both ends, and you kind of have an idea of what it's going to do. That's kind of the difference between electric and magnetic fields. Electric fields are just wild and all over the place, and you have no idea, right? You have to act fast and just be on your toes. Whereas magnetic fields, you have a better sense. They're a bit more controlled in the sense because they have to have, from that perspective, they're divergenceless. You actually don't have a single, what's called a magnetic monopole. It's never a jump rope held at one end. That violates the rules. In electric fields, you can. A one-handed jump rope is fine. So that's another reason why electric fields are much more unseemly. I'm sorry for the very crude analogy, but if people have oftentimes asked me, well, it's an electric universe. You got to tell me, why would you deal with magnetic fields? And I said, well, because it's a jump rope held at both ends. I don't want to get next to a jump rope held only at one end. You can't you have no idea what it's going to do, and it could do so fast. All right, so that's the crude analogy. So magnetic fields are extremely powerful because we can make a lot more sense of what they're doing, and we understand the stresses better. Whereas electric fields, they release their stresses so fast that oftentimes we don't, you can't see, a lot of times you can't see stresses build up. Okay, so now if we get to a beta gamma delta, again, it's the same kind of configuration that you see here, right? A beta gamma, you see it here, but that sunspot, right, which was in this case the same polarity, it's a different polarity. So now you've got this, what we call a delta spot. See what I'm saying? Okay, here's a beta gamma, but now you've got the idea of a delta spot. Or excuse me, not beta gamma, beta delta. Got the idea of a delta spot here, got an idea of a delta spot here. Okay. Now we go into beta gamma delta. Again, sunspot configurations look the same, but if you have a spot in the penumbra of the opposite polarity, like this spot here, even if the white light looks the same, it's not the same. And same thing here. Now they're showing a penumbra, and the reason why they're showing a penumbra in this case is because likely there's going to be one. But in this case, if you have the polarities that are very different, let's see, wait, no, what are they doing here? That is the same diagram, right? I've not looked at this closely enough yet. Why did they choose? Is there a spot here? I guess so. I guess they're trying to show, in this case, in this grouping, if there's a penumbra, which they would show here, it would be all one color, but it wouldn't be one color because they've got this here. But they're trying to show that same white spot. I'm not really sure what they planned, so I apologize. I'm not quite understanding what their point is with this one, the gamma and delta, because they had to change the diagram to make their point. Maybe here they're just not, they don't have any penumbras and they're too small. Maybe here they have a single, because this is what we're talking about here, is a single penumbra, obviously. And so perhaps the same configuration of spots can be there in white light. But if they have a penumbra and you've got spots that are entering from the different polarity, then because there's a white spot here you can't see, right? It's in that penumbra. And in this case, the penumbra is of the white spot, this little guy. And the two deltas are these guys. Okay, you'd think that they would own the penumbra, but in this case, they don't. Right? It's the penumbra of this guy. This is the penumbra of this little dude here. He owns the penumbra. It's his polarity, or hers, depending upon, or its, right? And so you're seeing, in this case, the polarity being violated or intruded upon by these two. These are the delta spots. So penumbras make a big deal when it comes to what you're calculating, especially when it comes to delta spots, because they have to intrude on a penumbra, okay? And Space Weather Live uses the Hale class for classifications, which is really nice. If you go to their site, and we will in a sec, you can see, I just pulled this up last night, you can see all the sunspot regions, right, the numbers here. You can see where they're labeling them green or yellow or red, and you can tell the class. So region 3806, which is what I think I have pulled up here, right? This is actually in real life a slider that you can slide back and forth between the white light imagery and the magnetic imagery, so you can get a feel for where those neutral lines are that you can't see in white light. Right? You can see the penumbras and stuff better in white light, where the umbra and the penumbra is. See, the umbra is that dark part, the penumbra is the slightly lighter part, right? You can see that in white light much better, because in magnetic field stuff, it gets covered because they're looking at magnetic field stuff, but you can sometimes still see it. And when I do my forecasts, oftentimes what I'll do is I'll have the white light composited with the HMI, and you will actually see the spot umbra and penumbra through the magnetic field. I typically have it reversed, so what you end up seeing is not a black umbra, but a white one. And so you see like a shade of gray for the penumbra, and you see that poking through a colored field, which is HMI. That's how I do it when I show the sunspots in my forecasts and whatnot. But as you can see here, beta, gamma, delta. Okay, because you've got delta spots in here that are invading the penumbra of others. Right now, it's the only one on the disk that's got delta. You've got beta and gamma, but you don't have any beta, gamma, deltas, just this one. And deltas is really when you wake up and go, okay, this thing could, depending upon the kind of delta it is and what the stress is doing over time, that tells you a lot. And I'm going to go to spaceweatherlive.com. This is what their site looks like. And if you go to solar activity, and you go to, where is it? Sunspot regions, sorry. I'm looking through the thing, I can't see it. Sunspot regions. Here you go. You get a nice little white light image that they've automated, so sometimes the numbers overwrite, sadly. But then below, here's all their sunspot regions. So this is live. Yes, they've got ads, so you have to deal with that, but it's still it's just an excellent site. Oh, and look, they've downgraded it. So the delta spots have kind of quieted down. And if you look further down, here's where they show you these images, just like I said. But in this case, because it's a live site, you can actually slide, get out of the way, slide the slider over. Isn't that neat? SWPC doesn't have the ability to do that. And it's not because they don't know how. They do know how. It's just not required, and part of their charter says that they can't. So a lot of times when you see the SWPC, you see other private sites or commercial sites that do so much more than the Space Weather Prediction Center does. There's a reason for it. They're limited. Their charter doesn't allow them to do that type of thing. But see, as you can cleanly see the penumbra, the umbra and the penumbra here, and then the small satellites. You have no idea what their magnetic configuration is until you slide the slider over, and you can see, whoa, see the blue and green right next to the red and yellow, right? And of course you have the foreshadowing, you have the tilt effect, right? The projection effect, because you're not looking at my flat hand here, because we're not near center disk. You're looking at kind of an angle. So the surface of my hand is tilted, right? That's what, if I were to lay my hand on the sun, ouch, 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 it's hot, it would be tilted, right? So you're not seeing this straight on. So everything is kind of squeezed together because of the projection effect. But nonetheless, you get the idea. You wouldn't have noticed that. It's this tiny little spot down here just below the penumbra. Do you see that? Let me try to make it bigger. A little bit bigger. See this cute little guy? Watch as I slide this over. Whoa. Okay. That's its magnetic polarity. It's the opposite. So what looks in white light to be extremely benign, whoop, hello. It's not so benign when you look at it in magnetic imagery. That's the power of magnetic imagery. We would be, as a matter of fact, anymore, I do not look at white light images unless I really need to understand the penumbra, the umbra and penumbra and where things are, and I can't see it in the HMI imagery. That's how often I rely just on this, okay, for better or for worse. Okay, another nice thing about, and I go through this in more detail later on, they show how the size is either growing or declining. They really keep great tracks of this. So it's just wonderful, and they do it for, you know, they keep track of what flares have occurred from the region recently, or for that you know, the amount of time it's been moving across the disk. And they do that for every region on the disk. See that? Look at it all. Okay? So you can go, like I said, I don't have time to go do all this. This is a cute one, though, because you can really see the polarity difference. See the difference? See, here you can see the neutral region, right? The neutral line's right about there where it flips. Here you can't tell. Okay? And you can see they look slightly different. They're in slightly different places. So it's not a perfect match, but, you know, probably because the images were taken at different times. Maybe one wasn't quite updated yet. There's all sorts of reasons for that. All right, let me go back to here. So hopefully that gives you a decent idea. And I'd have this as kind of a look back. This chart I include in, I included this chart in one of my mini courses a while back, might have been Sunspots and Telescopes again, because it talks very much about the classes and an example of this, and it's a good kind of overview of what these things are. And you can find this, a lot of this information, at spaceweatherlive.com in their help section. Okay, so it's a good site to go look through. It has lots of good information, especially about sunspot classifications in the classification scheme of the Mount Wilson, which is also called the Hale classification. Okay, there are lots of other classifications that you may have seen, but this is one that is used quite commonly. Okay, so, oops, we're going to move on to, well, I guess I can pause for a sec. Any specific questions on that? Okay, yeah, sadly not a beta gamma delta anymore, I know, yeah. So, yeah, I'm not going to, so is it similar to tornado development in the image? No, no, totally different. It has to do with the solar dynamo, and I've talked about the solar dynamo in past classes. So that's definitely beyond the scope of today's stuff, because I'm already taking way too much time to go through things. Okay. Looks like everybody's good? Okay, good. On Space Weather Live, yeah, Steffi, I agree with you. Space Weather Live is extremely helpful. All right, so now let's talk about coronagraphs. Okay, this was a snapshot I did of coronagraphs way back in 2020. There was nothing, nothing at all. Look, it's a completely pristine field of view, right? Makes you long for solar minimum if you're an amateur radio op. Well, I guess you wouldn't, because the solar flux was so low. But for those who don't like space weather events hitting Earth, it probably makes you go, oh, I long for those days. This is the LASCO coronagraph. These are white light coronagraphs. You're looking at two different fields of view. So this is the narrow view, and this is the wide angle. It's also called C2 and C3. That's why you see them numbered C2 and C3. Yes, they're always labeled red and blue. That's just a scientific code that they put so that when you look at the color, you immediately know what view you're looking at. Just the same thing as SDO AIA imagery. They color code them so that people know what they're looking at. Will this be the case in every spacecraft that has a coronagraph? I wouldn't count on it. People recolor things all the time. So always be aware what you're looking at, and what spacecraft and what instrument, because the colors could be different. The C2 field of view, that's the sun. Okay, we have an occulting disk that occults out to 2 solar radii. So basically this distance again, okay, 2 solar radii, 1 solar radii, 2 solar radii. And that's to block out all the really, really bright stuff of the corona, so you can start seeing out into the solar wind. The C3 field of view, as you can see, the sun is a lot smaller. The occulting disk is a bit bigger, right? It occults out a bit more. I don't know if it's four solar radii, but it occults out a bit more. You often see an occulting arm that's holding this occulter. Okay, this is not Big Brother blocking the view. It's an occulter. You can sometimes see it on C2, but you definitely see it on C3. This goes out 15 sun lengths, or 30 solar radii out from the sun, so you get a nice wide view. This only goes out to 6 solar radii, or 3 sun lengths out. Okay, so you get much more detail here, and you get to see the inner part of things. Much of this view is right about in here. Okay, so we use C2 and C3 to judge big coronal mass ejections as they come out. We also use these for solar radiation storms. And let me, before I jump to seeds, let me now go to, on Space Weather Prediction Center page, you can see the LASCO coronagraph under observations right here. Why they don't put the SOHO LASCO coronagraph, I don't know, but they don't. Things look a little bit different, as you can tell. Now we've got stuff that's moving, and it's because being at solar maximum, there's more going on. Now even here, I don't know if we've had, oh yeah, we had that one coronal mass ejection, that's right, going to the south of us. There it is. Is that right? 7. Yep, that's it. Ugh, I don't think it's going to hit Earth. And you can just barely see it coming out in the C2 or C3 field of view right here. right? It's going to continue to grow and get larger as time goes on. But you see it coming out in C2 before C3, obviously because C2 is going to see it closer to the sun than C3, so it will see it sooner. This is that coronal mass ejection that we saw in the SDO AIA imagery just a short bit ago. Doesn't look like it's going to be hitting Earth at all. I'm not sure, at this point I'm not sure if SWPC is going to model it. We'll see, because it looks pretty ordinary. Every now and again you see the flashes of black or data missing or something like that. Those are telemetry issues. Those are filter wheel changes. Those are, like that one there, those are spurious data that need to be removed. They are not aliens staring down the aperture of the SOHO-LASCO coronagraph. This poor instrument is coming up on 30 years old. Okay, it's unbelievably, the fact that it's survived this many years in space is unbelievable. And it's barely hanging on. I mean, the crew of SOHO-LASCO and just the crew of SOHO in period. This is a spacecraft that no longer has any of its gyros functioning. How they managed to maintain stable orbit is unbelievable, and accurate pointing at the sun is unbelievable, doing it gyroless. They have to do station-keeping maneuvers, and at that time they have to shut things down. They have to calibrate the systems extremely often to keep them functioning, because living and working in space for 30 years, you're going to get pretty sunburned. And these instruments have lots of trouble that they have to deal with. Sometimes we have CCD bakeouts on LASCO where they have to shut it down and heat it up to an insane degree to liberate all of the volatiles that have condensed down onto the cold detector. Because it creates a film, it creates problems for the detector to even sense the light coming in. So there's all sorts of maintenance things that they have to do with this spacecraft that take it out of operation for hours, if not days sometimes. And these are things that, in order to keep it functioning at all, they have to do this. It's not Big Brother taking this thing down. People who use this data, I mean, we use it all the time. This is a workhorse for space weather prediction. And anybody who bashes SOHO is on my poop list. And anybody who tries to say that SOHO, the data that you see here, is actually aliens or Big Brother hiding what's really out there. You guys are, you're not my favorite people. Because you have no idea what it's taken just to keep SOHO and LASCO alive and doing what it's doing. We desperately need to have a new chronograph. And I literally have a lump in my throat all the time I look at SOHO data, because if this thing goes out, we're in trouble. Okay, so we need to get another chronograph up there. We will with the follow-on, but it's taken a long time. So I am very grateful that SOHO and LASCO has managed to stay alive all these years. Because this is where our main information for CMEs come from, and how fast they get to us, and what kind of impact they're going to give us when they hit. Okay. Now, that being said, it's fun looking at these images, but you don't see all that much. Another way to look at them is to look at difference imaging. And there's lots of different platforms that do this. I'm just going to show one today, and I'll just go straight to it. I was going to show it on my charts, but it's called SEEDS. And a simple Google search for SEEDS CME will pull it up. Okay, it's from George Mason University, and it's a wonderful tool. There are two of them. There's one, SEEDS is one, Cactus is another. There are others, but these are the two that I use the most because they're the most robust. If you go, if you go to the SEEDS website, you pull it up. It's obviously made by scientists for scientists. This isn't really pretty front-facing, but if you go to the real-time module for LASCO and stereo, it does it for both LASCO and for stereo. I think stereo's down here. Okay, you can actually get a little grid that shows you where big CMEs have launched, or where the algorithms believes big CMEs have launched that are halos. That'll be a full halo will be red. Partial halos typically are in orange, and then the rest are just smaller structures that aren't, or smaller, narrower things that will not be a big problem, or at least the algorithm thinks that they're not big problems. I sometimes look at this. A lot of times I just go straight up here, and I'll just look at an entire day, because that's what these are. Now this is LASCO. They have one down below for stereo. Right, there's stereo. And sadly you can't get stereo B anymore because stereo B doesn't function. They still got it labeled, but you just can't click it, okay? But let's just look at LASCO for now. So this is today. And what's nice is that you've got the raw images for C2. It's only for the C2 field of view. But now you've got difference images as well. So when you guys see me pull this stuff up, or you see me using coronagraphs in my forecasts, this is what I'm doing. I'm taking movies of this actual movie. Okay, and so you can see this particular CME, whoosh, right there. That one is the one that was coming out in 211. Looks like it had a little bit of stuff happening beforehand. It's a little bit complicated. And then you get to see the cute little whooshes that are coming out of the top of the sun. There's some smaller coronal mass ejections that really aren't going to impact us at all. So my guess is NASA will model this. NOAA likely won't. They may, but I doubt it. Because it doesn't look like one's going to hit us. But this is a nice tool to use. Can you get more information from this? Yes, if you go back to that list, you can get an idea. Like if I click here on this particular one, they show it being, a partial thing, and probably this one, yeah. So what they do here, if I just continue to make it play, it will just play this over and over again, the part that they use. Now, the algorithm itself is looking, that's what the red and the blue lines are. It's showing you where it's finding the fronts to be able to dictate where, how it's going to calculate the speed, how it's going to calculate the position as it moves, what position angle it is, and how wide it is. So you can get that information from looking at this. The central position angle in degrees, how wide is it? Or angular width there, sorry. Central position angle is the central part of where the width is. That's going to be a single angle location around the clock. Angular width, how wide is it? That's what you see here. And then the linear fit, how quickly is it going? What I finally, and this is the velocity, and this second order fit will be likely its acceleration, meters per second squared. So these are the linear fits. I often find that off of the C2 field of view, SEEDS shows really slow speeds. Okay, they don't follow it up through the C3 field of view. So it's going to always underestimate the speed of what you would think that the CME will come off at. And that makes sense because it's just C2 field of view. It's going to show a typically slow acceleration. Okay, but you may not need this stuff, right? That's more scientific. What you need to know is it there, is it not? Okay, and that's what looking at either the event itself or looking at an entire day. And the neat thing is that you can go to previous day or following day if the following day has occurred, and you can stop and start using these aspects. You want to slow down, you want it to go backwards, you'll learn. It's really easy to use. Okay? And like I said, there are other ones, but that's a good one. So there's SEEDS there again. And so just taking a look at some imagery, when we actually had CMEs, here's a nice halo. You can kind of see it around. You don't really see it in the raw imagery. So these are taken just straight from SEEDS. Okay. Here's another one. Don't really see the CME very well. You sure see it. It's a full halo. Okay, in difference imagery. This is how important difference imagery can be. Again, in C2, this is where the CMEs are going to be the brightest. Kind of hard to see. You can see them when they move a bit better, but in the difference imagery, you can see them in stills. And in this case, I've actually labeled it. Okay. And of course, who can forget? If you look at C2 and C3 together, in this case I'm doing it through JHelioViewer, and I'll go through this later, not today, but you can get really high resolution imagery, right? So if anybody remembers this, that 8 CME launch back in May that gave us that G5, right? Notice it wasn't just one CME, it was a buttload of them. And I don't know how many, do I have all 8 in here? I might. There's Solar Storm 5. No, I only have the first 5 in this one. But at one point I had like 8 of them, and you could see the really fast one that was launched after. But this is an earlier version. I just grabbed it because it was close, it was easy. But as you can see, here's the C2 field of view, and I have it sandwiched with the C3 field of view. And so you can get really, especially when you do it as difference images, that's what these are difference images. So you can really see how big the halos get, and you can get a good sense of what the speeds are coming off of the disk, okay? And of course, you do see the occulting arm in the C3 field of view. Even in difference images, you will see it, especially when there's these flashes of lightning, that kind of stuff that you see, that like flash like that. That's anomalous data that then gets factored in the difference imaging, and so it makes these weird colors for a second, but it lights up that arm that you can see pretty well. Okay. But we'll talk more about J-HelioViewer and high resolution and compositing the C2 and C3 fields together later on. Most of the algorithms just work on C2. Okay, so if you see seeds or you see cactus, if you use those coronagraph data products, they just use the C2 field of view. Okay, another coronagraph to use as well as data, as well as imagery, is the stereo website. Okay, and here's what the stereo Science Center looks like. You can actually type in Stereo Science Center. Probably smart in a Google engine to type Stereo Science Center and spacecraft or sun. Something so that people aren't thinking stereo, ooh, you want, audiophile headphone stuff. No, because that's the problem with using the name stereo, is it's a very common name for a search engine. But when you get to the Stereo Science Center, it looks like this. Okay, you can see the flat map of what stereo sees, and then you will see stereo A. They finally cleaned it up. They used to have a big thing over here for stereo B that had no data, but they finally took that off, sadly, and just shows SDO, AIA imagery, and then stereo imagery in a line. And we'll go ahead and take a look at that. So let me pull that up. I'm going to kill Space Weather Live because it's making my system work too hard. I'll keep that, okay. All right. Stereo, well, see, I already had it listed, but let me Google it. Stereo Science Center and spacecraft. Okay, so hopefully you can see. Probably should have typed it in the other one so I could make it bigger. But there we go. Sure enough, first thing it pulls up. Right, so here you can see the Google search I did. Sometimes it's easier just to do Google searches than it is to actually have the links saved, because sometimes the links go dead. That's what I've learned with the wild, wild west that is space weather. Okay, so the Science Center, when you get to it, can look like this. If you go to latest images and plots, okay, that's when you get the page that I showed you, right, which you can look at the latest images and plots of both stereo A and SDO. Now, if you do, let's see, do I want to, yeah, I'll do this one. One of the nice things that's really good about stereo, about their Science Center, is that they've got an image tool, a movie maker, and that will flip you to this page. In here, and I'm not going to go through everything, I'll go through this in a deeper dive later. In here, you're looking at EUVI. This is an imagery. This is the ultraviolet stuff. This is like the SDO, AIA, or SUVI. Okay, that's what EUVI is. It's looking at extreme ultraviolet imager. Same numbers. Notice 171. That's going to be a gold sun. Well, I don't actually. The colors change here. I forget what color this is. It might actually be blue. I forget. So the colors change. 195, which is close to the 193, which is the bronze sun for SDO, AIA, and SUVI. It's a green sun here, okay? And this is the one that they have the beacon data for, which means real-time data. The others, you have to wait for days, and you get it several days stale. So stick with EUVI 195, and that will give you decent data. We're going to just pull up 512 resolution, okay? Because that's what it will display for us. You can download the other stuff. You want a slideshow, so it makes it a movie. Otherwise, you just get this massive list of images. Ugh. 2024, what is today? 097, so let's do 6. And then 2024, 090. I oftentimes go past the number. Let's do, because if you don't go too far past, it'll actually just pull up everything to the end, so you know you get everything. Oh, did I not select it? I thought I selected it. Select that, yes. Slideshow, okay, good. There we go. And there's wonderful SUVI stereo beacon data. Not high resolution. This is the low resolution stuff because it's the stuff that get to us fast, right? This is the stuff that goes through a very tiny pipe because stereo is used to being on the other side of the sun from us. Long distance, so it doesn't have a huge telemetry pipe, not like SDO does, sitting in geosynchronous orbit. This spacecraft is much further away and is going to get even further away. And so its beacon data is really kind of scrubbed down in terms of resolution, just enough for us to be able to do space weather, the qualitative space weather. No one would do science with this. Okay? And of course, what we're seeing with stereo is a little bit on the west limb of the sun, further than we can see, because stereo is now moving away from us, in front of us. It's pulling ahead again. Okay? But this is good to have, and it's a very similar display, like a JSON display, is just as you're kind of used to with seeds. And what's neat about it, actually I will talk about one thing. What's neat about it is that you can decide what frames you want it to do, and then you can have it swing, which is really nice. So let's say I wanted to go to, let me just go ahead and stop this. Well, actually, let me start it and go faster and see if I can see a nice event too. There we go. Where does it start? Yeah. 63. So let's do 55 to, let's do 70. Okay, so what I've done is I've typed in 2 frame numbers. And I do swing. What it's going to do is just rock back and forth between the two. It's a really useful tool, because if you're looking at some particular feature that you really want to see, sometimes movement makes a big difference. Okay, if you want to see this loop leave, or if there was a big CME that launched, I was hoping for that. You can actually see the extent of that CME, part of the CME beginning to occur here. See that stuff here? So swinging is very useful for that. And you could swing a long way or a short way. It's up to you. I just grabbed something simple where I knew something interesting was happening. Okay. So that's how that feature in swing works. And obviously just stop and undo it, and then reset if you want to go, reset these if you want to go further. Because otherwise what I think it does is it'll just go forward and then start again. See, so it only goes from frame 55 to frame 70 and then resets. So you can see just in one direction. So it's a powerful tool even with beacon data. It's kind of nice. Okay, another thing that stereo can do, so that's on disk imagery. Another thing you can do is you can look at chronograph data. You're looking at core. Okay, that's the chronograph. Now, core 1 is not very good. There was some damage, some problems with the mirror, so it doesn't look great. Core 2, however, is very useful. And you can either look at basic core 2 or the running difference of core 2. That's the same thing as the difference images. For beacon data, RD is much better. Running difference is much better than just regular core 2. Regular core 2 for beacon data, because it's low resolution, is really ratty. This is ratty too, but at least you see it a lot better. Okay, let me fast forward. After it loads, let me go a little bit faster. So now you can see that big CME coming out. There's actually 2 of them. One looks like they starts here and then it gets overrun by another. See, something happened and then you get a bigger one. And in that bigger one, the dim one, the one that really wasn't doing all that much, was a lot more wispy. That kind of disappears. It's not because it really disappears. It's more because with the bigger one, it's hard to say in this. Well, I can't tell because it's beacon data. But I think the imager changed its exposure, and so the weaker stuff disappears because now you don't see it because it's changed its exposure to capture to be more focused on this bigger eruption, which was brighter. So the weaker one becomes even dimmer in this imagery. Really hard to tell in beacon data. You almost have to wait for the science grade data. If I were to go back in time, about, I don't know, 6 days or so, let's go back to September 1st and do maybe to September 4th. What you will see is science grade data, and then it'll get ratty. Oh, that was a beautiful CME. Here's the fourth. Let's see if it makes it. No. Let's go to, and again, we're not analyzing data here. I'm just trying to show you how it works. Watch this. So now, science grade data, see how pretty? Looks nice. And at some point, the data will go and be really ugly. See if we can get, look, ooh, beautiful halo. Good Lord. Yeah, maybe we do have some big stuff going on. See that stuff? That's streaks. Those are anomalous things happening. That's not aliens. Those are. I have to go look and see what it is in the not differenced data. But yeah, you're making me want to go look on the far side because there's some interesting stuff going on there. Come on, show us. Yes. Okay, baby. Good luck. Have fun. There's the fifth. I think, are we at ratty data? Yeah, now we're at ratty data. Do you see how ugly that is? Really ugly data. So when it resets, you'll see how pretty. But see all the, there's pretty. Okay? And if I were to stop, God, that's really nice. That's 42. So if I go to, if I do frame start, actually, I don't think I can rock it back and forth. All I can do is let me just reverse it. So if I start and reverse it, watch how it goes from pretty data to ratty data. See how ratty it looks now? Because that's beacon data. So when you see that, don't think something's wrong. Just know that they just haven't gotten the science quality data back, down yet. And you're still dealing with beacon data. And typically beacon data will exist about 3 to 4 days out. So if you go back more than 4 days, you're probably going to get a good chance for science grade data, which is useful in certain cases. It can be, sometimes you can get the data higher grade data faster. I've had it do nice things, but not typically during solar maximum when the CMEs are too fast. But you see, if we waited for science grade data, then we could never use stereo as an actual space weather forecasting tool, because we'd be waiting too long for really good data, and we wouldn't see things like that, right? We'd be waiting 4 or 5 days, and we wouldn't even know what this looked like from stereo's perspective, right? And if you want to know where is stereo, nice, huh? Where is stereo? Well, you click it, and most of the time this thing is functioning. They don't have a really pretty plot anymore because they show too much. I think you can still get a plot where it's just the orbit tool, inner orbit. Yeah, there we go. So now you can see better where stereo is. It's pulling away from Earth finally. So it's got a bit of a view that's better than Earth. Stereo can see essentially the disk from stereo's perspective is this much. So there's this whole angle right here that it sees that we don't. Okay. All right, and you get lots of information as to where stereo is. Sometimes stereo is nowhere near Earth. Right now it's not too bad in terms of where it is near the ecliptic plane. Here it's just, they're slightly, a degree or two off each other. But sometimes Earth is looking up at the sun and stereo is looking down at the sun. So the angles that you see when you try to compare them A and B, you're looking at one is looking slightly above, one is looking slightly below, and it throws the perspective off, right? So certain structures that look squished in one look stretched out in the other, and you're like, ooh, how do I do this? It becomes really painful when you're dealing with like Parker Solar Probe or not Parker Solar Probe, but Solar Orbiter with its EUI instrument, because sometimes it's really close to the sun and it's at totally different angles. And when I do these synoptic sun maps and I try to put them together, literally the active regions, they'll disappear from one because they're down here, and then they'll show up on the next on Solar Orbiter, and they're up here. So even the imagery, even if you try to line it up the right way using all the mathematical prospects, the mathematical relationships in the same coordinate system, right, and everything, it still doesn't line up right, and that's simply because of projection effects. Okay, so be aware of that. That can not lead you astray, but just be savvy when you do that kind of stuff. And I can talk about that stuff later when we do a deeper dive. Okay. So there's stereo. Okay, so I'm going to jump into X-ray flux, and we'll talk more about that in a sec. Any questions on this? I see people thinking that the sun is just going to throw us a kill shot because of what? CMEs that you saw? Come on, guys, they're difference images. Halos are beautiful, and we get them all the time. We get CMEs all the time. Most of them are just minor inconveniences. Stop believing all the hype on YouTube. It'll rot your brain. It'll make you feel like, you're going to die tomorrow, and it's just silly. Space weather's been with us forever. The sun has been much, much more active than we see now. The sun, if we are just at a median, the average solar cycle that we've seen over the course of the last 25 solar cycles, it will be exciting. I mean, that tells you how quiet our sun has been. You guys have grown up in an era where the sun was sleeping, and you think that's normal. That's not normal. Our sun has been sleeping for the last 30 years, and that is the abnormal part. What's normal is more what it's doing now. Okay? But you've been conditioned to believe that the sun is supposed to be sleeping, and that's not the case. So relax. You're going to wind yourself and tie yourself up in knots and make yourself sick, worrying about it for no reason. Okay. The sun hasn't killed us yet. We even had a G5. And power grids went, hey, we can handle this. And I'm like, yeah, that's the effect of a weakening magnetic shield. Is that power grids go, hey, we can handle G5s now. Right. Okay. People think, oh God, because our weakening shield is, our shield is weakening, everything's going to fall apart. Certain things get better. Space weather is always a mixed bag. People have to understand that. All right. X-ray flux. That's where I was going. On the SWPC homepage, this one's easy. You literally slide down to this. Okay? Now, the fun thing, you can actually pop this big. Toggle full screen. Here we go. Okay, you can pop it big. Now, the fun thing is I'm going to go back to the charts in just a second because I want you to recognize something. There are typically two, maybe more lines, but two that you can separate. Sometimes you'll have extra traces that overlay, but they'll pretty much track each other. The reason for them are short and long. What they mean by short and long X-rays are basically the energy. Did I say that right? Short and long. Okay. The reason for that is basically the energy of the X-ray that's coming off the sun. Okay. Short means high energy, short wavelength. Okay, high frequency. Long means longer wavelength, lower energy. Longer wavelengths, lower energy stuff has higher flux, meaning there's more of them, more photons coming at us. So you will always have the long stuff be above the short stuff. Okay? Orange will be, in this case, always above blue because orange is labeled as long. Short is labeled as blue. Okay? And again, you're going to have, other spacecraft. So in this case, it's spacecraft 15 and 16. No, 15 and 18. 16 and 18, my fault. 16 and 18. I don't necessarily keep track of when they turn one on and turn one off. Right, this isn't a phenomenology course, so I'm not going to go off and say, oh, this is an M-class flare, it's an M2 level, and it's a long duration flare, meaning that it's got a CME associated with it. That's a different class, okay? But what you will see, I don't know why that's too long. Shorten this up a little. What you will see, though, is that SWPC has both the labels A, B, C, M, X, along with the actual logarithmic scale for the energy, watts per meter squared. It's a flux, okay? Energy per meter squared, I guess you say. And notice they're orders of magnitudes, log base 10, right? So each one is 10 times, each increment here, each tick on the axis is 10 times bigger than the one before. Okay, so this is a logarithmic scale, just like Richter scale, okay, just like decibels, right? It's logarithmic, which is neat because you need that big dynamic range. That's one of the neat things about X-ray flux is that it gives you such a big dynamic range to read over. because we need that. During solar minimum, we are way down here. During solar maximum, as you can tell, we are way up here. Okay. You will read the flare class according to the long X-ray wavelength, not according to the short one. It's the long X-ray wavelengths. Okay. If we read it according to the short one, this wouldn't even make an M-class flare. Okay. In actuality, this was like an M what? 6? M5.57, almost an M6. Okay, and you can see that when you look at the readouts. To have fun with this, here's what the X-ray flux looked back in 2020. Here's the long wavelengths. Look how low the noise floor was, okay? This is like at the A floor, okay? Oh, not quite the A floor, just above the A floor, below the B class floor. See the B floor? Right. Here's the C floor that I always talk about. I always call it C floor, isn't that cute? C floor. Here's the C floor. Okay. C class flares are when amateur radio operators might go, did you hear something? Right. When you get up to M class flares, that's when you have radio blackouts. R2 level radio blackout is at an M5 and above. R3s are at X class flares. And I believe an X5 or is an X10 is an R4. Might be an X, I can't remember off the top of my head. You can find that stuff out by looking at the data by the space weather scales. I'm sorry I'm spacing on that. I just had too much stuff on my mind and I just don't want to say something wrong. Is it an X5 or an X10? Oh, isn't that terrible? Maybe an X10 is an R5. I have to look that up. Because we happen so rarely, we don't have R4 level and R5 level don't happen all that often. So I don't want to misstate and then be pelted with olives. Okay, at any rate, so what I want to show you here is this is where we were back in 2020. This is why we need such a big dynamic range. We're down at the 10 to the minus 7th range, okay, essentially. That's the B class floor. If I go back, well, actually I think I can go forward. Here was yesterday. I took this one from yesterday. I put them on the same scale so you can see the same levels. Our short wave is higher than the floor of the long wave during solar minimum. Our long wave is sitting above the C floor. Okay, that's at 10 to the 4th, 10 to the minus 4th, 10 to the minus 5th almost. No, 10 to the minus 6th rather. Sorry. 10 to the minus 6th is the C floor. So we were well above the C floor. We're almost at an M class level. If you notice, you can see that. That's how high we are right now. An M class level on this thing is clear up here. We weren't even popping flares at the level that our noise floor sits now. Thank goodness we have lots of solar flux, because otherwise radio propagation would be nil. But thanks for solar flux, we can handle higher noise floors and still get decent propagation. But that tells you the difference. Funny thing is, this is either complete dropouts. I think this here and this here periodic and this here periodic, they kind of look like the same. These might have been eclipse periods. We're going into eclipse now. I think we're in eclipse season. That's where these things drop out. See this? It drops out. See this? It drops out. Right, if I go back to here, yeah. I think these are dropouts because we are getting the moon beginning to pass over the imager as it looks at the sun. And so we're going to have these flux dropouts. These happen several times a year. Don't worry, the instrument is not having any problems. This one, in fact, was likely a close where the instrument was only partly eclipsed, and so the dropout wasn't total. But you're going to see those periodically. They'll be very consistent because it's just the moon passing between the spacecraft and the sun. Because GOES spacecraft are in geosynchronous orbit. You don't get that with spacecraft that are out at L1, that are outside the moon's orbit, right? It has to be an orbit that's closer to Earth than the moon. So, okay, I'm trying to think if there's anything else I want to tell you about this. The only other thing about this data product is you can choose how quickly you want to look at it, right? So if you want to spread out for one day, you just click the one day tab. If you want to do even more, you can drag and highlight and it will zoom in for you. That's oftentimes handy when you want to try and find where the peak of a flare is and what the level is, right? Because sometimes it's painful. You can reset it easily, toggle full screen again, and I'll, for instance, highlight this. So here's the peak of that flare, and it looks like, indeed, 5.57 was the peak. Okay, so that's what it's useful for. All right. And of course, we're looking at solar flares, right? This is when the sun screams, and the sun screams only on the day side. So solar flare data is only useful for the day side. It's not going to be useful for the night side. If you're at night, you're not, and if solar flare occurs, you won't notice. Okay, so don't worry about it if you're on the night side. Next one will be radiation storms. Again, another data product that works very similarly. This is from, these are energetic particle storms, so these are relativistic particles. In scientific vernacular, they're called solar energetic particles, SEPs, but they're also called radiation storms in the layman's vernacular. SWPC has a nice warning threshold. It sets it up for us all. This is only one of 2 warning thresholds. This warning threshold is for this line, okay? So think red and red. But there are other lines, as you can see. SWPC even bragged about the fact that they put a greater than 500 MeV line on here, which will likely, if almost never, rise. Even in this cycle, probably won't rise. Maybe next cycle, if next cycle's bigger, it'll rise. But we won't see it here because our SEPs have not been all that energetic recently. What we're looking at with the different colors are energy levels, just very similar to the X-ray flux where we had the long and the short. One is more energetic than the other. Right. The longer stuff, the lower energy stuff, will be the stuff that has the highest flux levels. So this is going to be the lowest energy line. In this case, it's above 10 MeV. Okay. This is what we call integrated flux. I think I'll wait and go into what that means in the deep dive. Because I don't want to get stuck in the minutiae here. I just kind of want to show you how the instrument works. With this flux level, right, this line has to get above basically what we call 10 PFU. That's particles. This is a what we call a PFU. It's protons per square centimeter per steradian per second. Okay, it's a flux. Meaning it's how much goes through a certain space in a certain time with a certain amount of energy, that energy or above. Okay, so it's counting the most number of energetic particles because as you go higher in energy, there's less flux, there's less of them. So all of these fluxes here are being counted in this line. You may not see it go up because we're orders of magnitude lower. As you can see, these are 10 to the 4th, 10 to the 3rd, 10 to the 2nd. So we are once again doing it in a logarithmic scale. But there are actually 2 thresholds. This threshold is the S1 threshold, okay? But it only applies to this line. We also have a 1 particle per, and that's 10 to the 0. This isn't 100, this is 10 to the 0. We have 1 particle per, or one PFU threshold to get to an S1 level for the green line. Okay, that's 100 MeV. So if either the red line gets above 10, that's this 10 to the 1 here, or the green line gets above a 1, that's what 10 to the 0 is. It's a 1, believe it or not, 1 PFU. Then we will be at an S1 radiation storm level. Okay, most people don't realize that there's actually 2 thresholds. SWPC is only putting this one here because this is the easier one. This is the one that's breached more often. It's more rare to have big radiation storms with what we call a hard spectrum. Most of the time, these are pretty quiet. But you will see in big radiation storms, strong ones in particular, you will see all the lines crawl up. It'll be interesting to watch how the 500 MeV line rises. Typically 500 MeV are saved more, that's more for galactic cosmic ray flux, which is what you're seeing here as a background, likely. I'll say that with a caveat that I'm not sure how much electronics noise we have in this. or even just regular instrument noise. But as you can see, we do have a near, this is what I would call elevated levels just below the S1 level. And this was likely an east limb or behind the limb event because of the slow rise. But that's phenomenology, and we'll talk about that later. This was likely, this is a second event. Surprising event to see. Okay, let me go to, here's what it looks like today in real life. I just picked that up yesterday, so it's not much different. Okay, so this is the live number. And just like the other ones, you can highlight certain sections to look at them more closely. And it will give all the levels, all the numbers for you. Okay, but likely for space weather forecasting, you just want to look at this. This is something that in DRAP will light up the poles. This is something in neutron monitors that will give you higher fluxes. Okay, sometimes for short-lived periods, especially if it's super energetic. You see these particles go up, then you will see neutron monitors, you'll see a peak because you get cosmic ray showers that really are intense. And you can get something called ground level events. But we'll talk more about those later. Okay, kick out of this. Any questions on, I guess I'll stay here because I'm going to go into interplanetary space. Any questions on this stuff, guys? Any specific questions on any of the solar or interplanetary, or excuse me, solar only stuff that we've talked about? The line plots, I will clarify, the line plots here, obviously are not solar imagery. These are also from the GOES spacecraft, but they're sensing, they're looking at the sun, and they're getting information from the sun, either X-ray flux that they integrate over to create a line plot, or particle, they're catching energetic particles that are being launched in a radiation storm. So still solar stuff, but it's now stuff that has traveled to Earth in 8 minutes or under an hour, if it's particles, okay, energetic particles. Okay. I'm reading. I heard Tamitha mention that this is Arnold, but I guess it's too soon to determine the extent of the damage. It cannot be repaired because of AC voltage spikes. And are we talking about Discover? I don't know. Yeah, I'm not sure. Is there a chronograph instrument that launched with GOES-U to help with SOHO's retirement? Or did I misunderstand? There, on GOES-U, maybe. I mean, that's part of the space weather follow-on, then yes. But I don't, I mean, I have to go take a look, to be totally honest. But we are definitely looking to retire this thing. And we've been trying to get chronographs on instruments for on the GOES spacecraft for a long time. They keep getting kicked off. So I apologize for not keeping up on everything. Do I know whether it's going to be up? If you is the one that's coming online, I didn't think there was going to be a chronograph on that one, if that's the one that's coming online now. But I will look. I would think that they would have chronograph first light images, because they're showing first data from GOES 19. They're showing magnetometer data, but I didn't know that there was a chronograph on that one, if that's you. Yeah, there's SICE. I'm seeing SICE, which is energetic particle. I would think that I would know. I hope I'm wrong, but I don't think there is. At least not on the one that they just launched. But I will look and dive into that. We'll look at that more in depth when we do the solar deep dive. Okay. So I apologize, I can't answer that right away. Okay. What affects DRAP more, X-rays or protons? They both do. They affect them in different ways, which we'll talk about here shortly. I'm going to be talking about that when I get to the ionospheric stuff, so let me hold off. Can I ask, years ago a large asteroid broke up and fell into our star. Could it cause these types of disturbances, flares and the like? Nah. I mean, it'd have to be a massive thing. I mean, if you remember Shoemaker-Levy that smashed into Jupiter Jupiter just went, okay, and swallowed it. And Jupiter's a lot smaller than the sun, so you can imagine, most likely the asteroid didn't even make it. It probably melted before it even got to be able to penetrate. That's what typically happens with both comets and rocks and things. I mean, rocks melt. You just have to get them really hot, right? That's what lava is. So if our Earth can do it, the sun can do it even sooner, even before the dang thing penetrates. So, the impact that it has, it's not going to cause anything big. Nothing like a lot of these stories, these movies say that it's going to do. Yeah, that's well, like I said, we've seen them a lot with comets. Those are big asteroids coming in. So it's not going to be, well, they're not big asteroids. Most of them are ice. So it depends upon what the asteroid's made of. But all things considered, it's pretty minor. The asteroid, like I said, Shoemaker-Levy, that broke up just in the Jovian gravity field, then smashed into Jupiter with 8 or 9 different impacts. Jupiter just absorbed it. And so it makes me think that maybe at the very bottom of Jupiter, in the very core, we always say it's just a liquid core. Makes you wonder, is it totally liquid? Or there might be some solid in there with rock? I don't know. It'd be very interesting. Don't know if it's hot enough. But that's all planetary stuff. It's way off topic. So that was my best answer for the moment. Okay. Let's see. Good. Very understanding. Awesome, guys. Goes you will be goes 19. Yeah, so I'll have to take another look. I don't recall there being a chronograph already, but we'll see. The last goes was launch does have a chronograph. Jesse, Okay. I'd love to see them test it out then. Come springtime. Okay. Well, let's hope. Let's just cross your fingers. I knew it was a follow-on. I didn't know if it made it on Goes You. Like I said, I don't follow that stuff super closely just because I'm spread so thin. But I knew it was coming. But let's hope. Let's hope. All right. Oh, my computer. Is it fried? No, it's not fried. It's just got... Because my studio is so complicated and I've got all sorts of things running NDI tools and everything, it resets stuff. That's the problem. Is I've got a lot of stuff and interfaces that have been reset. And when I had it functioning this morning, I had it functioning in one way, in one particular mode, and then I switched modes and it blew up. So I realized I've got other stuff I've got to set up. So that's my problem. But it's the thing is the computer itself isn't fried. It's just I have to start over in many areas. Okay. Any other questions, guys? Yeah, I know. I needed a UPS. My UPS, I bought 2 UPSs and they died very quickly. I don't know if I have bad power in this house or what, but it's a problem. And so I have not gotten another UPS since my other one, my more recent one died. It is what it is. All right, interplanetary space. Let's jump into this. Okay, I don't have a lot. Now, the solar was by far the largest set of things, okay? Interplanetary space, we basically just have a couple things I'm going to show. One is going to be the Enlil, let me make sure, let me not misspeak. Yeah. We're just going to show basically solar wind and Enlil, okay? So this is a tool that you see me use in my space weather forecasts all the time. It's a tool that basically it's not data, it's a model, right? And it uses inputs, and I'm not going to go into the super details of what it is, but it uses inputs at the surface of the sun to understand its magnetic complexity and other things, other parameters. And then it also propagates that information out into a three-dimensional sphere, of which we take slices of. Okay, in this case, we're taking a slice through what we call the ecliptic plane, which is basically cutting it in half. In this slice, in this slice here, we're cutting it vertically, and what you're seeing is just a segment of it. You're not seeing all the way. They don't make it. In this case, they're just showing a foreshortened area. They're not showing the full 180 degrees of a cut that goes down the Earth-Sun line. Okay, so this slice, this is why when you see me label them, I have north up here, south down here, and when you see me label here, I have west here and east here. This one, you're looking down at the sun, right, from the North Pole. That's the North Pole of the sun. The North Pole of the sun from this perspective is here. The south pole of the sun from this perspective is here. Okay? And Earth is always the one that they show here. The other two dots that they show are stereo A and B. Okay? This is stereo A, stereo B, sadly, dead, defunct. Okay? Sometimes you'll see magnetic field lines, but we'll talk more about that in the deep dive. This pinwheel type stuff that you see, these are fast wind streams. It's actually the stream interaction region if you're looking at the top panel, because this is density. If you look down at the bottom panel, this is velocity. And where you see colors going up closer to the red, that's where the fast wind streams are. Okay? Where you see the colors dipping into the blue, that's where the slow wind streams are. Okay? And when fast wind reaches slow wind, here and here, you're going to get big stream interactions here and here, where the density goes up. And you're getting one here because this wind is so slow, and this isn't much faster, but it's a little bit. So you get a... And same thing here. Slow wind in the blue, faster wind in the green, and you can see a density increase here. So these are the stream interaction regions that kind of act like solar storms sometimes, if they're strong enough. And it will rotate around kind of like a water sprinkler that rotates. So you see these pinwheel kind of effect. Okay, it's the Parker spiral. That's what you're seeing in these in these things. I will show you a movie of what it looked like when we had all those CMEs launched back in May. There's like 4 or 5 of them. Boom, 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 boom. In this model, okay, I'll pause it. In this model, you see multiple things. First of all, you see the panels here and here. Okay, this is the density. So this set of 3 refer to this top panel. This set of 3 refer to the bottom panel. Okay, and what you're seeing is the plasma, because this is density. So you're seeing the plasma density, solar wind density at Earth. It's stereo A, which is that dot up there. Or excuse me, in this case it was clear back here. And stereo B, which is here. Sadly, we can't check with stereo B because stereo B is dead, but SWPC still has it in their model. Okay. In the case of this, and when you see coronal mass ejections, you will oftentimes see them crush in together. That is a artifact. I want to call it an artifact. It's a feature of this model. You see, like, for instance, these two coming together. Here they merge. It's not what happens in real life. They crush, they spoon, they distort, they bend, even parts of them begin to merge together at the edges, but they don't annihilate each other. They just don't, because there's magnetic field there. Here, the magnetic field is only on for a ride. It's only there as a placeholder. It sees other magnetic field goes high, and the other magnetic field goes right through it. That's not realistic. Okay, in real life, the magnetic field sees the other magnetic field and goes, whoa, ho, 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 stand off there, pal. Don't get too close, don't invade my space. Right, and so they fight each other, whoa, whoa, whoa. That's what happens in real life. But models like that have that real acting forces, magnetic forces, run too slowly to be real time, to get ahead of real time. Okay, so we use something that makes a lot of approximations. So this model is not perfect, but it's the best we can do ahead of time. Okay, now things are coming online. People say, oh gosh, this thing's been around for a long time. Yes, we are working on a ton of models that are going to supersede this. But it takes a long time for those models to get developed in the academic arena and then be tested in the operational test bed, because they were born out of academia. So there may be lots of places where they can break, right, or get hung up, or all sorts of weird stuff that then can't work as an operational model. So they have to test and test and test them to make sure that they're useful and can be employed in an operational sense, and that takes years. Okay, so we have a lot of potential models that are coming up through the ranks that are better than this, but they're still all being developed, and so this is still the state of the art for now. Okay, reading these plots, you can see the density goes way up when this CME, when this crushed CME reaches Earth. You can see the running time. That's the now line, and boom, whoop, That was cute. Don't know why it did that on me. Come on. Let's get it closer. There we go. So you can see as it's crossing, at least with Earth and all these others, it's almost happening at the same time. You're seeing where the density peaks, and you can see the time. You can kind of see what the level of density is, but I wouldn't trust this again, partly because the data is, you know, the model itself is not completely realistic. You can get velocities. If you go down to the bottom panel, you can see how the velocities, look how strong they are, right? Clear up here and close to 1,000s. Right, that says 900 right there, if you can read that. So then you get velocity profiles again at Earth, stereo A, stereo B. Okay? Hopefully that helps you read it. Again, the bottom panel is the same as the top panel, it's just that this is velocity. So this is the west limb over here, this is the east limb, or at least that's the west limb, that's the east limb here. West limb, east limb, and then you just stretch it out. So west, east, here, north, south. Here's Earth. And this is what the profile of the thing looked like as we slice right through these structures, slicing just like my hand was a knife, slicing right down through the center, okay? And these are days. So you're seeing the velocity profile or the density profile unfold over time. To take a look at a less interesting, I'll show you in a second. To take a look at a less interesting model, there are no CMEs in this model. How do I tell? Well, that's a good example of telling, but that's not the way I tell. There's a very big tell. You can tell whether or not SWPC has run a model with a coronal mass ejection in it or not. How do you tell? Down here, it will show you its mode. I've had so many people tell me, oh, there's a CME there, you can see it, right? See, it's right there, it's right there. And I look at the model run they show me and it says this. And I start cracking up, going, try again. Ambient means ambient conditions, ambient solar wind. They have not launched a CME in there. This is the wrong mode. They can't launch a CME when it's ambient. Okay. So here they're just modeling the solar wind. You can see, in this case, a very large coronal hole giving some fast solar wind all through here. If I go back to my charts, I don't think I can zoom in. What mode is that? CME mode. Right. So if you want to know whether or not SWPC has modeled a CME in a model run, you can go to the page, take a look at that model, and if it says ambient, they haven't done it yet. You don't even have to load the model. You can just have it sit there and spin. Okay? How do you get to this page? Products and data, models, WSA Enlil. Wang Shili Argy. That's some of the inputs that they put into Enlil. And Enlil, the magnetic portion of it is Dushan Ostrasos. Enlil is a god of some kind. I forget what he named it after. Cheeky bugger. Dushan is a wonderful person. One of my favorite heliophysicists. So you don't even have to load it if you see ambient and you're looking for a CME. They haven't done it yet. And apparently this version of Enlil loads a lot more, or churns a lot more slowly than the NASA version for a certain reason. And they do use different, if you looked at the NASA models versus the NOAA model, they do use different versions of Enlil. And so when I say versions, Dushan made me be careful. They're not really certain versions. The Enlil model is the Enlil model. It's just that you can toggle things on and off inside the Enlil model to change the parameters around according to what you think, what you want to use, what you want to emphasize. NOAA emphasizes very good predictions for the ambient solar wind because they care so much about streams. But there are other things that then causes it to slow down, and other processing things that make it different than NASA. NASA cares about getting predictions off quickly because they have to protect human flight and the human component. And so they have a different agenda. And I've talked about the reasons for that in the past, and I'm not going to take the time to do it now, but we can do that in a deep dive as well. I probably will talk about their motivations are different. So the versions of Enlil they use are different. And the speed at which the model outputs, get to the public and become public facing are different. SWPC almost always will be after NOAA. And SWPC will almost always be after NASA, after the M2M. That office will get stuff out much faster. But it's not because the SWPC guys are lazy, it's because they're doing different modeling for different reasons. And their model is different and it takes different compile time. Or rather run time, not compile time, but run time. Okay, their models run slower because of the choices that they've made with the Enlil model. All right, back to my charts. Okay, any questions on Enlil? Yeah, stereo B, I know, sad. It's sad. So the top left and bottom right view, just different info, as is the top and right bottom left. They're an X pattern crisscross. I'm not sure what you mean by X pattern crisscross. This being, where's my ball here? Oh, here's a ball. Oh, okay. So, in this case, usually I say this is Earth, but in this case it's not the Earth. This is the heliosphere. We're making it a ball, okay? If it were 360, whoops, let me come over here, make it super big. Okay, so if it were 360, please forgive the ring light there. If it were a full sphere, right, that's what it would be. Take it off like that. That is a cut through this ball this way, right down the center. Slice the ball in half, right through the center, okay, and you will get this. So it's literally taking this ball and slicing it. If I took a blade and went and cut this ball right in half and you're looking down, that's what you're seeing, is that. Okay. In this case down here, go down here and put the ball up here again. Okay. You're looking at the same thing, but now we're going to look at velocity. Okay, so this is density, this is velocity. Okay, same way. Now, if you want to talk about these, now we've taken a ball. If I take the ball like this, okay, so that the edges match. If I can get my fingers out of the way, see if I can get let me put it this way. See how the edge, I'm trying to match that edge right there. Okay, and what I've done is instead of slicing sideways, this ball, if I look down at the North Pole of the sun, looking down here, I slice it this way. Okay, I'm slicing this half, and this side will be Earth. The sun's North Pole, I'd be looking just straight down from this line, right? The South Pole straight up from this line. Earth would be here. The North Pole of Earth would be here. The South Pole of Earth would be here. I slice it along the Earth-Sun line. So I cut it in half this way, and then I only show you this half. Got it? Just this half. Because I care about from the center of the sun out to Earth. Center of the sun out to Earth. Okay, well, and beyond, slightly beyond Earth. Okay, so that's what I mean. That's the north. So that's why when I label it north and south, I label it north and south. Okay, you're getting a cut through the ecliptic plane that goes completely north and south. I take this ball, and in this case, I cut. I should do it this way. Hold it with this hand. I cut from the center of the sun all the way down. Okay, that's this. But the north part is here, the south part is there. Okay, hopefully that makes sense. Cutting it along the Earth-Sun line. That's for both density and velocity. The two panels are exactly the same, it's just what they're showing in each value is different. Okay, and it gets even more complicated when we look at how NASA shows theirs with their footprint, with their what's called their splash screen. But we'll talk about that. That's a ribbon on the outside. Hopefully that answered that question. Okay. So satellite 1 is broken. Oh, we're still talking about it. All right, I'm not going to talk about stereo B right now. They do the best they can with what they've got. No past the Helios for the Voyagers are in interstellar space. We think. They're not in pristine interstellar space yet. It looks, we're not quite sure if they've passed the bow shock yet. They're maybe in the shocked plasma of the interstellar region, but they're definitely out of solar wind, heliospheric solar wind. Okay, why does a solar wind speed? This is Henrius. Why does a solar wind speed usually increase after the density peak? Because what we're dealing with, if we're talking about here, just in solar wind data, what we're talking about here is you've got slow solar wind in front, you've got fast solar wind in the back, and the peak will actually be in between because that's where you're compressing. The fast solar wind is slamming into the back of the slow solar wind, and it's causing a compression region. We call it a stream interaction region, and that's where this line is. That's what this line corresponds to. So it's not after the fast solar wind, it's ahead of it. And how it looks in, oh, this is not a good example. Whoop. That's not a good example either. Poop. Yeah, because we're outside of it. Shoot. Is there any other place? How about there? No, it's all the. None of that's good. The best example I can give right at the moment for stream interactions is if we're looking at stereo. Let's look at stereo A. So that's the red line, red thing here. That's the red line in the middle. Okay. So don't look at Earth. Look at red line. Because stereo A is just now inside, at the very beginning of the model run, stereo A is just inside that fast wind stream. Okay, it's just beginning to get hit, and you can see the speed of the solar wind here is really high. But if you look at the density, it's really low. It's actually kind of coming down. You can kind of see it coming down a little bit. What it's coming down from is a bigger stream interaction region, which is like a bump in the density. That's from this. Okay. This is why I say stream interaction regions and fast speed wind act a lot like solar storms. In fact, sometimes we have a hard time telling whether something is a stream interaction region or an ICME, a solar storm, because they look, sometimes they can look very similar. But you can see stereo A is just coming out of the stream interaction region, right? So the density is still kind of decreasing. It was probably a lot higher, it was up to here, if you followed that trace up. But it's just now entering the high-speed wind, which is a chaser. The high-speed wind think of it as a chaser to the stream interaction region. Okay, and that's why when we get activity on Earth, it's oftentimes before the high-speed wind kicks in. Then when the high-speed wind kicks in, typically at high latitudes you still get activity, but at mid-latitudes, if there was any aurora going on, for example, it pretty much calms down during the high-speed wind because there's not much else going on because we cared more about the density and the compression of the solar wind than we cared about the speed. All right, hopefully that answered that question. Arnold, why are you worried about my studio? The age of my facility, it's my house. And I'm a single point failure, so if I don't have a UPC at the moment, what do you don't worry about it. I'm fine, I promise you. Yeah, I hope you're not a troll. Try to say, oh, she can't do anything. She's in an old facility and she really should just retire. I hear enough from you guys. If you're going to be disrespectful, I invite you to leave. You don't have to be here. Okay. Jaredobi, I'm sorry, I'm butchering your names today. Hi, is there any reason they should change the position of the satellites closer to Earth? The satellites changed because of the mission. These were the stereo satellites, and they are actually on their second time going around. They actually were going around the Earth. Stereo A was going ahead, it still is, going ahead of the Earth, and it wrapped around, and now it's coming back. Stereo B went behind, that's what the B stands for, it went behind the sun, I said behind the Earth, sorry, behind the sun, and is now has come back and is going behind the sun again. Sadly, Stereo B is dead. During the conjunction phase, which was back in 2014, 2015, when they went through this, what they call the superior conjunction, where they were passing behind the sun, there was all sorts of stuff that they had to do to prevent their feed horns, their antennas from burning up because they were pointing at the Earth. They even were using sideband for a while because they could only point their antennas kind of partially to Earth, because otherwise pointing them straight at the sun would end up burning them up. So they had to kind of go into this configuration and had to change how they did everything, and even had to turn off for a short period while they were here. Well, Stereo A, as it went behind the sun, came out just fine. Stereo B had a gyro failure. And when it came out, it just messed everything up. And I can go into the details of it some other time, but we tried recovering it once. We actually did make contact with it, and trying to fix it, that's when we discovered the gyro failure, because we sent it into a worse tumble. And now there's just no hope, because all of its hydrazine was frozen, and so it couldn't even try to straighten itself out. Poor thing. It's just, it's awful. So it's a real heartbreaker when we realized that what we were trying to do to fix it actually exacerbated the problem and made it impossible for us to recover it. So, okay. Let's get back to the topic at hand, shall we? Now, okay. Destruction Warehouse, you are correct. I just don't have patience because I'm already time limited. We already talked about this. I'm time limited and I have to stay on topic. And if you're just going to say rude things, what's your point? Okay, so now let's talk a little bit about the solar wind, right? I always talk about our upstream monitors, and what do I mean by that? Well, some of you probably know what Lagrange points are, and some of you don't. Lagrange points are places where we can take advantage, at least in a two-body problem, we can take advantage of the gravity wells that are created. Okay, so if we take a look at the gravity field, the combined gravity field of the sun and the Earth, you'll notice that all these contours kind of lead to certain points where there's crossover, right? An inflection point here, or a concentration of the gravity at a particular point. Okay, these wells, as they're called, or inflection points, as they're called, create unique points in this system that are fixed. So as Earth rotates to here, okay, we have the sun here and the Earth rotates here, this whole system rotates with it, okay? It's really cool because that means that L1 point, even if Earth is up here, L1 will be just in front of Earth. Even if Earth is over here, L1 will be just in front of Earth. And if it rotates over here, L1 will be just in front of Earth. It rotates with the system, okay, because it's Earth's, and it's the combination of Earth's and Sun's gravity. There's a point at which Earth and Sun's gravity essentially equal each other. That's L1. That's where you see it crossing over. What that means is that it's a unique balance point. It almost acts as if it's another solid body right there, with which you don't park a spacecraft at that point. It's like landing it there. That's not stable. But you can orbit it. You can orbit that point as if it's another body that helps keep it in orbit. So you reduce, now granted, it's not very much of an effect, but it allows you to reduce the amount of gas or fuel you need to stay stable. And because that point rotates with the Sun-Earth system, then it drags the spacecraft along because that body that it's orbiting moves, right? So it kind of just takes it along with it. And so we find that quite useful. There's 5 of them. We use in space weather, we use L1 quite frequently. We do not use L2. This is for those deep space people. James Webb Telescope, right? Lots of others. Ones that need to stay in shadow, the infrared ones, and in particular the ones that have to be shielded from the sun because of contamination. L5 is one that sits, this is one of the wells, so these are like inflection points, L1, L2, and L3. L4 and L5 are slightly different because they're actually wells. They actually have, and are they more stable? I don't know. That's a good point. That's a good question. But L4 and L5 are L4 and L5 are extremely useful because stereo has shown us that if you park something, let's say at L5, you get a view of the far side of the sun a bit more than Earth does. Because your disk, as we call it, remember we've talked about an Earth-facing disk? Well, here's an L5-facing disk. See how you use disk? Disk becomes very important. Here's an L3-facing disk. It's the exact opposite of an L1-facing disk. Here's an L4-facing disk. Okay, got it? So an L5-facing disk actually shows part of the far side compared to an L1-facing disk, right? Because you get this whole section in here of the sun that you can't see from Earth. So this is where vigil goes. And this is the one I'm paying much more close attention to than the GOES U. Sorry to say. After the Discover debacle, I kind of like wince anytime somebody talks about GOES. Plus, I've sat on some independent review teams for GOES, and the GOES R block, and it was very painful. So I have a lot of history that I don't mind not looking at when it comes to the GOES spacecraft. So yeah, maybe it's my bias there why I don't look at it as much as I should. Okay, anyway, so we have these Lagrangian points, as they're known as. Okay, and L1 is where ACE and Discover and SOHO with LASCO sit. Well in front of Earth, about 400 radii, 420, 430 Earth radii ahead of Earth. And it always stays there. And as you can see, there's lots of L1 spacecraft. You can see them all here. They have wind. Not even wind is, I'm not sure wind is at L1 right now, or if it's, they hijack wind and move it all around. Sadly, it was called wind. And for a while, it became a magnetospheric thing and was doing loops around the moon, for goodness sake. But wind might be back at the L1 point. I'm not, I don't know what its path is right at the moment, but I do know it's sampling solar wind, so it's very useful because it's got really important instruments, just not real-time instruments, sadly. We don't get real-time data from wind. So it's a key location, L1 is, for our spacecraft. And again, we orbit them, right? They orbit L1. You don't just park there. So when I say park, I'm using it in a loose manner because you actually are orbiting. But this is why if people say, well, how, isn't it getting full? How can you have so many spacecraft parked at L1? Well, it's because they're orbiting that location. So there's lots of space. We can park more people, more things there. Okay. And when we talk about the upstream monitors, that's what we're talking about. This is why when something hits a spacecraft, hits our upstream monitor, hits ACE or Discover, right here's ACE plus Discover right now, or in this capture, we have time before it hits Earth. Okay, how much time? Anywhere between 15 minutes to 60 minutes or so. 15 minutes if the solar wind is extremely fast, 60 minutes if the solar wind is extremely slow, right? It's a function of the solar wind speed. So let's take a look at some real-time data. In Space Weather Prediction Center, you'll see it looking something like this. This is old data. This is from back in 2020. Again, solar wind was really weak at that time, so magnetometer data is showing only 5 nanotesla. Really, really weak. I'll get to ACE in a second. To get there, real-time solar wind. Okay. Okay, so this is what the data looks like, and sorry I have it on a white screen. I didn't bother to redo it. I wasn't expecting to do it on this screen, so it's white right now. Solar wind, sitting around for total magnetic field, and I'll talk about these panels in a sec. Total magnetic field sitting at about 5 nanotesla, a little bit higher. Okay, we don't have much going on right now. And that's labeled in BT in black. Okay, you can toggle. You have total field. You have the X, Y, and Z components in these different colors. What's neat is that you can toggle them on or off. Boop, boop. Okay, and each one of these components means something different. The reason why it defaults to be total and be Z is because for geoeffective structures in the solar wind, you always want to know what BZ is doing. Okay, it's the basic geoeffective, the most geoeffective component of solar wind structures. Is it the only one? No, right? BY can cause big issues for us depending upon what's going on. BX can even cause issues, and at the equinoxes, BX matters a lot. But this again isn't. I'm not going into the details of solar wind structure right now. This is just more about the data product itself. Okay. Now, I will talk a little bit about this stuff, and then I will show some examples just for fun, and then I will refer you to a mini course because that will go into a lot of the phenomena that everybody wants to know, which is how do you tell when a CME hits or an ICME hits, in this case an interplanetary CME. We call them ICMEs because they're in interplanetary space. They're no longer being looked at from the sun. So we distinguish them from a coronal mass ejection because we're not looking at imagery, we're looking at in situ data. And the structures are different. They look different. And you can get them confused especially if you're talking about them in the same context. People don't know, wait, are you talking about the imagery or are you talking about the in situ stuff? And it looks totally different. So I will be as careful as I can to say ICME when I'm talking about an interplanetary manifestation of a coronal mass ejection. ICME. Okay? Some people just call them ejecta. Some people are lazy and just call them CMEs. I get it. Either way, they're all solar storms. Okay, that's a layman's vernacular. Now, the top panels here are showing the orientation. Okay, you can either get it in Cartesian coordinate system for the magnetic field, because we care about the magnetic field orientation, which tells us the orientation of the obstacle. The reason for that is because it is very typically a solar slinky, right? It comes off of the sun, boing, sorry, it's white, so you can't really tell, but it comes off of the sun and comes out something like this. And again, I will refer you to a course that will talk more about that. But when you look at the magnetic field, okay, with all their components on there, looks like a disaster. You don't have to look at, if you prefer angles, you don't have to look at the Cartesian coordinate system. You can look at the angles. Now in this case, I think they only show phi, but if I switch or I ask it to, it might show theta as well. The phi angle is the angle that they use to determine whether the sector is towards or away. And that's because the phi angle sits in the ecliptic plane and is essentially, it's in the XY plane. So you're talking about BX and BY. This is still an angle of the magnetic field orientation. But it's telling you whether the angle is, and because I think they've got it 360 good. They've got it oriented 360, and I'll talk about it more in a sec. But depending upon the angle of that in the ecliptic plane, what that angle is defined as, it will tell you if the magnetic field is pointing, if that's the sun, pointing away from the sun, or if it's pointing toward the sun, okay? That's where you get this towards and away sectors. These are important, again, when you're looking at the equinox, because the same kind of thing with that polarity of the coronal hole where I said plus and minus, right, towards and away. Yeah, same thing. See the plus and minus? Do you see the pluses and minuses? It tells you what's going on. Away is a plus, towards is a minus. And the reason for that is because the way the magnetic, the coordinate system that we're using here has been defined. And I'll talk about that in a sec. Density of the solar wind. Okay? Average density goes from, a typical solar wind goes from very low, like 1 or 2 particles per cc at the lowest, to around 10 particles per cc, right? Or per centimeter cubed, if you want to look at it that way. For average. How high can it go? CMEs, you can get 30, 40. Big CMEs, 50, 60. Close to a shock for a big fast CME, close to 100. You're getting up to hundreds. You get close to hundreds, and you're going to be getting a pretty strong storm. Okay. Yeah, I'm not going to go. I mean, I could go on, but I'm not going to. But that gives you an idea of how this works and where it is. As you can see, it's sitting in a logarithmic scale. Always pay attention. Some things are linear, some things are logarithmic. Depends upon how much dynamic range this stuff covers. Okay. Next panel is speed. Speed of the solar wind. And these things are just like everything else. You can zoom in and get a zoomed in picture. You can adjust the markers and all that kind of stuff. I might go that, I'll go into that in the deep dive. Here I just want to make sure you understand how this thing works. And then you can, you know, get the speed or the density, or if I move back up, the colors are representing the colors, you know, which component you're looking at. So 9 nanotesla total, but 6 of it is BZ, positive BZ. 6 of it is it's positive. Oh, sorry. No, that's should be this way. It's GSC. Oh, because I switched it. Okay. I'm glad I looked at that. Towards and away, this is still aligned in terms of the sun. So the coronal hole notation that you saw in the sun and the synoptic charts, that is consistent with this. It is not consistent with the GSE coordinate system, which we'll talk about in a second, because positive magnetic field is towards. So the X component, which is red, if it's positive, that's not going to be away. That's going to be moving toward the sun. If it's pointing away from the sun, it's negative. So when red goes negative, okay, that's actually pointing away from the sun. So don't coordinate this with positive, negative BX, okay? And we'll see why that's important in a minute. It's just simply because you shifted the coordinate system you're looking at. This coordinate system is sun-centered. This is not. This is GSE. It's not sun-centered. Okay. And then temperature is the last one. Don't worry about temperature, to be totally honest, unless you really are an advanced learner and you're looking for the core of a CME or an ICME, for example. If you're looking for the solar slinky core, oftentimes the temperature will go down. Not always, but often. As our solar cycles get bigger and bigger, the core will be more visible. The whole ICME will have a low temperature. That's the way it was back in the 80s and 90s. We had really beautiful magnetic clouds, which we still don't really have much of yet. But I think next cycle might give us that, which would be really nice. Makes our job easier because the events get more extreme and we're able to see them easier. Last couple cycles have just been brutal. Okay, but that's an aside. Let me go now back to here. I won't go over ACE right now. We can go over ACE. I'll go over ACE in another time because I want to keep moving. So what are we talking about with GSE? What are we talking about the theta and phi rather? So the GSE coordinate system is centered at Earth, or in this case, centered at L1, right, just ahead of Earth, close enough. But it's centered at the spacecraft, which we just basically call Earth in this case. X is in the direction of the sun. It's basically the Earth-Sun line pointed toward the sun. Positive is toward the sun, positive X. Negative X would be facing away from the sun in the GSE coordinate system because the center is at Earth, okay? Geocentric solar ecliptic. Y is pointed in the direction of opposite of planetary motion. So in other words, it's in the ecliptic plane. The ecliptic plane is the plane where all the planets, orbit, okay? So Y is always pointed the opposite of planetary motion. Negative Y is the direction Earth is moving around the sun. Z is northward, okay? In this coordinate system, if you are wondering what is, I've got it backwards. Phi and theta, you've got it, I just used this label, my apologies. They've got it set up as phi being theta. Am I correct? You're calling it phi. Oh, and you're in GSM. Oh gosh, you're really. Oh, and this is in GSM too. They don't have it in GSE. What do you guys have? Well, I guess it's important to have it in GSM. These are, we're splitting hairs here. The problem I have is, maybe I should use different angles, definitions here. GSE, that's where you see a lot of when you're in the solar wind, we oftentimes use GSE. When you get into the Earth's magnetic system, you switch into GSM coordinates, and the reason why is because Earth's magnetic field is tilted just a smidge. What that simply means is that we take this Earth-Sun line and we rotate this coordinate system just a little bit and shift it. So X and Y are, Z and Y are slightly changed. X stays the same. It's a, yeah, I should have paid more close attention. Like I said, I have power outages. So you do need to pay attention if you're looking at, because for instance, I bet you this, whoops, that's right, it's just a slide. That's probably in GSE. A lot of ACE data may be plotted in GSE. We have to be careful. Yeah, and that's all GSM. Okay. What it does in real life here is that your Y and your Z components will be slightly different. Okay. Are you going to notice it? Not really. I mean, I've even seen published papers that have missed. They're using data in a GSM coordinate that should have been GSE or vice versa. So even scientists make that mistake sometimes if they're not careful. You can get caught. If you looked at GSE or looked at GSM data, will it make a big difference in terms of space weather forecasting, whether there's going to be a big storm? No, don't worry about it too much. It's more the details of it. A big storm is going to cause a big storm no matter what. So essentially, it's so for the work that we're doing right now, it's close enough. Okay, so like I said, it's slightly shifted. This shift just a little bit based on the Earth's magnetic field tilt. But the angle that we want to define is going to be this angle. And I'm sorry they put it as theta. I just pulled this off the web. I should have paid closer attention. I should have switched these two, because theta in space weather is typically labeled as a latitude coordinate, where phi is typically the longitude coordinate. So pardon me here, but so what we have for the phi notation, and I almost really want to switch this, that's why I'm standing in front of the letters here. What we're looking at is the longitude, okay? That's what this is. This is the longitude, okay? So whatever you want to define, whatever label you want to use for that particular angle, it's the longitude. It is defined in the XY plane. So that's the ecliptic plane, okay? It's defined from X equals 0 in a counterclockwise fashion all the way around to 360 degrees, okay? So I say here it's defined in the XY plane from a plus X direction in a counterclockwise fashion all the way around. So certain angles that are close to 0 or close to 360 are going to point toward the sun. Certain angles that are closer to 180 are going to point away from the sun. Okay? So if you have a vector, a magnetic field direction, and they're saying a point P, let's say the vector is like this, and it's got a certain X, Y, and Z component, which you see in the solar wind data, it will also have a phi component, or a latitude, or excuse me, a longitude component. I'm covering the label because in SWPC they've called it phi, okay? But it will have that component that goes 360 degrees as an angle that helps define. That angle will be sitting in the ecliptic plane, and it draws out to, as you can see, point Q here. So it's like if P made a shadow, if the sun were shining down, if you made a shadow onto this ecliptic plane of this line, this point, then what is the angle from that X axis to that point? What's that angle? That is the longitude. Okay, it's in the ecliptic plane, and it's basically there only to help people determine, is it pointing away or is it pointing towards? Okay. Now, once again, we get more complicated because I thought they would have defined this in GSM. They defined it according to the sun's positive and negative polarity, so that they could line it up with the synoptic charts. But we can dig more into that in a deep dive, okay? I grew up with cutting my teeth with X, Y, and Z. I prefer it more than angles. If you want to know what the other angle is, they oftentimes label it. If you see it, here it's going to be labeled phi, and then the latitude will be labeled theta. In my nomenclature, sorry, I had it backwards, just because the diagram I took off the web had them labeled, so I just used their labels. But the latitude will be only defined from 0 to 90 degrees, and it will go all the way down. Okay. So 0 degrees latitude all the way down to 90 degrees. So you can get solar wind data defined and shown in a plot having a magnitude, okay, so just B total, and then both a phi and a theta angle, a latitude and a longitude angle. And that's it. No coordinates, no X, Y, or Z. All it's doing is just a different way of displaying where the same point is. Are you defining it in a coordinate system that's Cartesian with X, Y, and Z, or are you defining it in this case, a spherical coordinate system that's got a magnitude, which is the length of that vector, the strength of the magnetic field, and then both the two angles give you the unambiguous location of that vector. Okay? And that's all it is. Examples of solar storms in the interplanetary medium, I decided to give you some examples. Right, you can see them very quickly in the magnetic field components. Sometimes a lot easier to see in the magnetic field components than any of the other components. Again, labeled X, Y, Z. Right, I have phi here, I'm not paying attention to phi. I have phi here, I'm not paying attention to phi. I don't particularly use it, I don't really need to. I'd rather look and see when BZ is less than 0 and what BY is doing. Okay, and that's what you're seeing here. Notice the speed jump, very typical. Density can oftentimes drop in these structures, but not always. It becomes more chaotic, that's for sure, typically. But here's some ugly storm times. Here's another one. I don't know if you can see this. It's a much prettier storm. Here's, I've got all three components you can see going here, and you can actually see some level of rotation. Here's BY, the blue, rotating. Okay. That rotation, if you have BY rotating from positive to negative, and if you have BZ, where is it? BZ is what? What color? Red in this case? Gosh, I can hardly see it. Red, I believe, in this case. And it goes up and then down. This is actually a very nice coronal mass ejection, ICME, and it's a slinky. It's in this case what we call an east, north, west CME or ICME. You can see the nice jump in speed that goes down. Density, like I said, can get kind of chaotic all over the place. Temperature in this case went down just a little bit once we got in the core. This is the magnetosheath, so density was still high. Looks like I need to move my camera a little. Where is that? I'm getting a little bit of a light leak, so I want to make sure that's not too much of a problem for you. I think I got one more. Here's a pretty one. Again, XYZ. In this case, it looks like total field. Yes, total field is red. Don't always expect the lines to stay the same, the colors to stay the same. They don't always. Okay. In this case, we've got BZ, I believe, down here. And again, there's an orientation. You're seeing a rotation here. You're seeing rotations. I think the BY is going from west to east. So big rotations. These are showing that there's a solar slinky in there. Okay. And I talk about what that means and how to orient yourself in a different Q&A, in Q&A C2. Okay. So this was Interplanetary CMEs and the truth about Carrington events. This is in the C mini course series. I strongly advise you to go look at that series because it's got all sorts of good stuff in it. If you want to know more about modeling, or not modeling, but understanding and trying to figure out what you're looking at in these in situ solar wind plots when it comes to big solar storms. I walk you right through it, and your friends will think that you are a magician because you'll be able to predict what these CMEs, or what these ICMEs rather, look like hours in advance after just seeing the front end of it, especially if it's a well-behaved structure, because it will have a very certain signature and it can only be one structure. And you'll be like, you know what, it's going to do this. And for the next 12 hours, we're going to see this. And when you're correct and other people kind of look at you like, whoa, how did you know? You're like, well, you know, it's magic. Really, it's not. It's just thankfully the ICMEs have a beautiful magnetic field that's consistent and stays reasonably well behaved when these structures are strong, what we call low beta structures. They stay strong, they can be very beautiful and have very coherent magnetic field structures. This is me explaining one of my old papers. You see my little can diagrams. Chris Mostel has done a much better job since then. This was many years ago. He's taken that whole thing and just blown it out. Him and Amelia and a few other interplanetary scientists have really done a great job creating very, very graphically beautiful solar wind, CME structures coming out into the solar wind and then flying over a spacecraft and then tracing out the magnetic field lines. And we'll go into the Austrian Space Agency and talk about their models later on. That will be something we'll do in the deep dive for the interplanetary stuff, because Chris has got some of the best stuff in the business. Okay, and that is the end of that part. How you guys holding up? You guys, is it making any sense? And oh, poor Lisa, she's, oh man, I just got home. Yeah, we're knee deep in it, I tell you. Let's see. Okay, thank you for the great explanations. You're very welcome. The vectors can measure the weakening of the magnetic field caused by heat and velocity. Not really going to be weakening of the magnetic field. You're talking about Earth's magnetic field? No, this is these spacecraft are outside the Earth's magnetic field. So you're not getting any weakening of any magnetic field unless you're talking about the, let me go back to, there we go. Unless you're talking about the structure of the CME. And you're really not talking about a weakening of the magnetic field if you're talking about these ICME structures. What you're really talking about is the expansion. Because as these structures expand out in the solar wind, they've got to get bigger, right? They get bigger, much more large azimuthally than they do radially, just because of the nature of spherical expansion. And so as they expand, it's kind of like the same thing in the solar wind. You're blowing up a balloon, and the more space you've got to fill out with the same amount of stuff, the weaker the stuff is, the less dense it is, and therefore also in the magnetic field, the weaker it is. And so as these structures continue to expand outward, they will look as if their field will look as if it's weakening, because as it's flying through Earth, the structure is so massive, by the time the tail of this structure passes through Earth, the front of it has already expanded a whole bunch more. So the structure itself is much, much further out in the heliosphere, right? Because these structures can be as wide as a quarter of the distance from the Earth to the Sun. That's how big these ICMEs can get, okay? So when you're talking about a structure that's that large, by the time it finishes crossing Earth, that structure could be, was on its way to the asteroid belt, for goodness sake. It's almost at Mars, for goodness sake. So it's so much larger than it was because it's had to expand as it moves outward. And therefore the magnetic field goes down. So don't look at these structures as if you're seeing a snapshot of the actual structure. As it blows over Earth, and it takes 24, 36, 48 hours for even the really, really big ones or the composite ones, as it takes that long for them to blow out and blow off of Earth, you're looking at an evolution of the structure in time. You're looking at an expansion of the structure in time. You're not looking at a snapshot, right? So it's like when you started watching a child grow. You saw them when you first looked at them and they first came into your orbit, looked at you. They were 6 years old, but it takes so long for them to pass your field of view that by the time they pass your field of view, they're 15. It's like, well, how big is the kid, right? You get confused. You're like, okay, well, wait a minute. The kid was 6 and now it's 15 and it's still the same kid. Is that a snapshot of the kid? No, you'd never think that. You'd realize, oh, it's growing. Same kind of thing. It's an evolution of this structure in time. So you're not looking at a snapshot. And you have to be careful when you imprint or you assume that any of these, especially the big ones, that any of these are snapshots of a structure. They're not. Which is one of the reasons that makes single spacecraft observations of these structures very tough. This is why we don't understand them all that well. And why they can still get away with twisting and contorting and we can't make sense of them. It's because we only have one eye to look at. And yet the structure really needs an armada of spacecraft at different locations to be able to understand it fully. Okay, so a lot of ambiguity in the observations. I hope that makes sense. Steffi, you said, oh, apologies for the mistype. I didn't even see it, so no worries. Okay. Great, well, great so far, well explained. I'm definitely going to need to rewatch all of this. Well, yeah, and when I do the deeper dives for each component, it will get better because I'm just laying the foundation, and then as we dive into deeper, you will already have that foundation upon which to build. Physics is not easy, even conceptual physics. It's not easy. It takes a little while to get used to some of these concepts. And so the best way to do it is to hear it over and over again. And that's not saying anything strange. I mean, this is what we do with students, even in college. You know, you start them off with the basics, and then you revisit those same topics time and time again. You know, at undergraduate level, and then at an upper division undergrad, and then at a graduate level, and then again at a graduate level, and you just keep building a little bit more complexity each time. And that's kind of what we're doing. So, oh, thank you. Life Force says riveting. Wonderful. Excellent. Yes, making sense. Good, good, good. Okay, and yes, sadly, I can't go into all the details. I'd love to. I mean, I'm already really late as it is. But there's so much wealth of information in space, in situ data that we don't get from imagery. Okay, because they're almost two different animals. This is why I'm very careful to say coronal mass ejection and interplanetary coronal mass ejection. Even though in layman's terms I say, oh, it's a solar storm. Okay, fine. That's the non-expert term. But when we get more specific and we're trying to talk about data products, it gets better. It's smarter to be able to separate that out a little bit. Okay. And knowing all of this terminology, whether it's expert or non-expert, if you kind of keep them all in your mind together and just use them interchangeably, it helps other people learn too. Okay. It also helps teach scientists to sometimes use the non-expert terminology so that people don't get lost. How much mass was ejected in the 2024 event leading to the Aurora in Texas? Which event? You're talking about the May event, I'm sure. Off the top of my head, I don't know. I think the average mass is something like 10 to the 15 kilograms or something like that for a typical coronal mass ejection. This one, I don't in particular, I don't know. But that isn't what Earth saw, right? Earth, you know, this thing is so much bigger than Earth, and Earth is like a pinpoint, it's like a pinhole flying through this structure. And the amount of mass that it was able to, you know, inject into our magnetic system is minuscule compared to how much mass the whole thing actually has. So, you know, and some of that, of course, is stood off by by the nature of the dynamics of Earth interacting with this structure anyway. But that's a conversation for a different time. Okay, yes, and Lisa, good point. Yeah, that was a succession of multiple CMEs getting all spooned together, right? Right, good. Thank you for reminding me that. Too many physics involved. This is why I watch one over and over again. Yeah, I know. I'm pulling in from a lot of different sources and a lot of different times. Okay. Teresa, my brain keeps trying to figure out how this works in the micro versus the macro with the sun and the Earth. The sun has to be doing these things for the benefit of the planets, especially ours. I need to review. Yeah, and that's a very general question, right? Because macro versus micro. I mean, micro can be really teeny tiny. And the neat thing that you see in space physics at least, or in heliophysics, is that you see the same processes over and over again on different scales. So you'll see the same thing happening on different scales. What the stuff, how eruptions occur on the sun, and they throw these big coronal mass ejections at Earth. That eruptive process looks very similar to how Earth's magnetic tail sheds some of this extra energy once it's thrown into Earth's system. Earth itself goes through a reconnection process and an eruptive process, in a sense, and sheds these big plasmoids. We call them plasmoids. And what they really are? Slinkies. They're just little versions of the big CMEs. And so the processes are happening on a fundamentally different level, or they're different size, different scale size. But the fundamental physics involved ends up being very similar. So, if you're getting confused because you're seeing similar things happening over and over again, you're like, wait, I thought that was with that. Maybe I'm wrong. No, it likely is that it's with both. Okay, so the macro scale and the micro scale oftentimes can, as long as it's not too tiny, right, and you don't break paradigms, right? We're not going to the quantum mechanical level. We're not going to the kinetic level. As long as you can still behave as a fluid, in this case a magnetohydrodynamic fluid, then there are lots of things on different scale sizes that you'll see over and over and over again. Okay, which actually is one of the beautiful things, because it means that if you understand one side of the structures and the physics, then you can apply that knowledge in another area and still have some, cogent understanding and intuitive ability. Certain things won't apply, right? Because we don't have a solar wind blowing out of Earth. It's more like our atmosphere leaks out, but not it's not being blown off. But nonetheless, there's still a lot of other fundamental things that are similar. So hopefully that helps. Okay, how many deep dives planned? As many as we need. How's that for each area regime? Okay. All right. Does current science have the idea that the sun is hollow? No, we can't look inside the sun, sadly. We have to look to the great gas giants to give us an idea. We can't get below the radiative zone, even with helioseismology. So we look at the gas giants to be able to get a better feel for what's going on. And what we're finding is there's a lot of Earth-like components, talking about, seeing the same thing over and over again. There's a lot of stuff that people know in terrestrial meteorology that is applicable not only to the gas giants but also to our sun. Rossby waves are a classic example. What we see in our upper atmosphere is something that helps cause hot spots, what I call hot longitudes. Those are Rossby waves bubbling under the surface that are actually helping get those magnetic submarines buoyant enough to pop through the surface. And that's why we keep seeing them in the same location. It's because the sun's surface moves over these areas of instability. And these areas of instability just keep bubbling up new ones, but they keep bubbling them up in the same longitude over and over and over again. Except from, longitude is viewed from Earth. So it's very interesting. There's so much we don't know, but if we point some of our scientific know-how into the realms of the big gas giants, I think we're going to do a lot better. And if we pull in more meteorologists, terrestrial meteorologists who understand how fluid dynamics occurs in atmospheres, whether it's neutral or not, those rules still apply. Gravity still plays a massive role even at the sun and in these gas giants, even if the stuff that we're dealing with is a charged plasma. That just adds electric and magnetic fields to the mix, doesn't take anything away. So the other rules do still apply. And so if we pull in these people with that kind of expertise into heliophysics, I think we're going to make some breakthroughs when it comes to our star. But we just haven't done that yet. We're too busy focusing on astronomy and astrophysics and looking at those fields saying, help us with understanding solar physics and understanding our star. We really need to look to the meteorologists. But that's coming. That's coming. All right, let's go into magnetosphere. So here's an example. And I'm not going to spend much time on this. We'll go this in a deeper dive, but there's a couple things that I want to show. So for the magnetosphere plots here, this is actually a movie. You're seeing a pretty calm magnetosphere. Let me go straight to what we have now. Magnetosphere, where are we? Okay, we go to models. Go to Magnetosphere movies. Whoop, I'm in the way. Geospace Magnetosphere movies. Come on, give us something. And sadly, I may not make it today because we're already at 3.5 hours. I just thought I could do it. I'm so sorry. Okay, so here's Magnetosphere. It looks like a good Lord mess right now. Okay, so if you go to the Space Weather Prediction Center, why I'm showing the Magnetosphere is you'll see shortly. Not so much for the models themselves, but rather what they stand for, okay? And you have multiple planes, multiple different parameters that we're looking at. So it's the same magnetospheric model, but we're looking at different things. In this case, we're looking at pressure, okay, in nanopascals. So this is dynamic, well, yeah, probably dynamic pressure inside, probably. Maybe not. But maybe it's not dynamic pressure because it's not really, it's moving, but it's not like the solar wind ram pressure. Here we're looking at density, particles per cubic centimeter, and you can see the density going up in blue. I'm not going to bother with those. All I'm going to bother with is the solar, is the speed of the velocity of the wind in here. I call it wind. I shouldn't call it wind. I got to be careful. I have something on the mind that I want to talk about, so I have wind on the brain. I'm going to play this for right now. Let's see what we got. Oh, we got some fun bumpity. Okay, you probably can tell right off the bat that the sun is over here and the solar wind is pushing against this structure. If you couldn't tell that, you should be able to tell that because this is the Earth and they're showing the night side of the Earth in black, the day side in white. So it's like it's daylit. From that, you should be able to tell that you're looking down at one of the poles. This will be the North Pole. Okay. This is the equatorial plane. So now we're in the plane very so much like the ecliptic plane, but now it's the equatorial plane based on the magnetic field of the Earth. Okay, so the magnetic field has its own orientation, and that the equatorial plane is where the magnetic field, it's where if on the Earth you would have a neutral line where you're mapping around. So just like the geographic equator, this is the magnetic equator, okay? You take that plane and you spread it out in space, right? You just extend that plane out into space, and that's what this is, okay? Now, solar wind is coming in. You see in red. Notice it says negative, okay? It's because this is in GSM coordinates. Negative means, negative means blowing away from the sun, right? If I go back to, you guys are going to be so confused by the time I'm done here. If I go back to here, pretend this is now GSM. If you have solar wind blowing this way, it's going along a negative x direction, right? Because positive x is toward the sun. Negative x is this way, okay? That's why it's negative. Solar wind is blowing this way, okay? Now, the solar wind is hitting an obstacle, as you can see. No, it's not a jellyfish, although it looks like one. This is the Earth's magnetic system. Is this data? No, please. Please don't have anyone tell you that it's data. It's not data. We don't have a ton of spacecraft measuring all this. This is a model, okay? It's taking the inputs from one of the L1 spacecraft and it's importing it into this, okay? And there's lots of other complex stuff going on in here, okay? But this is one of the main inputs that it's taking, this is solar wind input. And so you can see when stronger solar wind comes, boom, it hits this thing. When lighter solar wind, backs off either in speed or honestly in density, this thing will billow out. So push, the solar wind's strong, it crushes it down. When solar wind is weak, it billows back out. This is the standoff right here. You can actually see it sometimes push in. Look, that's the standoff. That's the front of the Earth's magnetic system. As you can see, it's very dynamic. Comes in and out, in and out, in and out. Can come in and out quite a bit. These labels are in Earth radii. We all call that RE, okay? RE. So you can see sometimes the standoff distance goes well beyond 20 Earth radii. Sometimes when the solar wind goes away, it can get really stand off. It can stand off quite a ways. When we have a strong solar storm hit, this thing can crush way in. Okay? And there's some models out there, there's some model runs showing how it literally stripped, with a Carrington class event, stripped us in so far. We were down to like, for those who were in the know, into like L of 2, L of 1.5 to 2, enough to stand off the solar storm from stripping our atmosphere off in any significant manner, but not far enough. We lost our radiation belts, that's for sure. That was pretty fun. Anyway, we'll talk a little bit more on that in a sec. So why I'm talking about this? Well, there's two reasons. One, I want you to see how much this magnetopause, as we call it, that's the magnetopause, that place where it stands off, how much that moves in and out. Okay, so that's one thing. The second thing I want you to see is, look, there are places where we have blue. Whoa, blue? That means this direction, right? This is where infamously I've been pointed to YouTubers that go, the solar wind has changed direction, folks. This is the end. I told you the sun is collapsing. I told you the sun is going to go micronova. I told you the Earth's magnetic field is weakening. I told you, and now you're seeing it happen. Okay, first of all, this isn't solar wind, okay? This is the magnetosphere. This is the realm of the second chef. The job of the second chef is to scramble the eggs that the sun throws at us. This is not the solar wind. This is not the regime. This is not the first chef's kitchen, okay? This is not your son's kitchen. This is the second chef's kitchen, and unless you know what you're talking about, you really should stop, because you're making it harder on the rest of us who are trying to keep people sane and not scared. This speed, these bursty bulk flows, okay, happen all the time because this structure is like a slingshot. You pull the slingshot back, and you whoop, let it go, and you shoot particles forward, and guess what? They go into the North Pole, and then they go east and west, and here, in this one, they go into the North Pole and the South Pole. I forgot to remind you. This is in the equatorial plane. This one is in the noon-midnight plane, which is the same thing as slicing this one. Remember how we talked about with the sun, how we did a north cut, south slice? That's what this is. Noon, midnight, meridian. Okay? Whoops, so sorry. This one, it goes this way. We slice it down like this, and we lay it out this way. This is the North Pole of Earth. This is the South Pole of Earth. Okay? The position we're looking at Earth from is from dusk. In this plane, dusk is over here. Dawn is over here. The sun is over here. Okay? As the Earth rotates, the sun rises. As the Earth rotates, you see the sun on the dawn side. As the Earth continues to rotate, the sun disappears at dusk. Okay? This is the dawn side. This is the dusk side. Here, we're looking at Earth from the dusk side. The equatorial plane, this plane that you're seeing here, is actually a flat plane this way. Got me? So now we're looking down at Earth from the North Pole, up at Earth from the South Pole. This is the night side. And what do we do with that slingshot? Not only does that slingshot pull back and shoot particles this way and this way, but that slingshot pulls back, and from this plane, it shoots particles north and south, and guess what? That's aurora, okay? These are bursty bulk flows. A lot of times I will call it a wishbone. You will see a straight line and then a fork this way and a fork this way. This is following the magnetic field. And you'll see there's the wishbone, see it? Right, let me go back. And this is just from some random model today. This happens all the time. There's no solar storm happening. There's a wishbone. Let me see if I can pause it. There. You got two kinds of wishbones. You got an east-west wishbone, and you got a north-south wishbone. Okay? This is not solar wind, folks. This is the second shift scrambling up anything that's thrown inside. This is normal. It even has a name. Dipolarization. Oh, it has another name. Substorm. Okay? It has another name. Low Earth orbiting satellite destroyer. Charger. Satellite operators don't like these. Okay? But it happens a lot. Why is it happening here? My guess is that because we had a lot of electrons shooting. Why do I say electrons? Because they're moving onto the dawn side. These are where these are where all the protons are going. But all the fast-moving, what we call motorcycles, are going to the dawn side. And you will almost always see injections of flux from the tail going onto the dawn side. But they also go north and south. You have to follow the magnetic shield. The Earth's magnetic shield is complicated. The heart of it looks like this, with Earth in the middle. You tell me that doesn't look like a particle accelerator. Okay, the Earth sitting in the middle like that. That's a particle accelerator. What do particle accelerators do that are round like CERN? Things go round and round, round and round, round and round. This kind of looks like I'm stirring something, doesn't it? See why I call it the second chef? See why I say it's a near-Earth mixing bowl or a near-Earth skillet? Because of the magnetic field. Again, the magnetic field orders everything. Okay? So, that's the second important thing about this. And I'll go into the other parameters in the deep dive. But what I want to show you is this. Here's a movie. Here's the May 10th. So was this the whole thing? No, but it was part of it. Guess what this cute little guy is? I'm going to call this a GOES spacecraft. It's sitting almost around... Am I in the right place? Well, I guess I have it a little bit further out than I should. I've got about 10 RE. It's supposed to be about 6.6. Meh. I had to, it's awfully big, so I had to kind of compromise. But it's sitting out at geosynchronous, give or take an ish. What does it do? If it's on the day side of Earth, what does it see? Well, it sees the second chef doing its thing. Except when the magnetopause, as you see here, squeezes in too far. Which you will see for a second. Ooh, right there. Now what? Now what is it seeing? Is it seeing the Earth's magnetic shield? Possibly not. It's seeing a mess instead. Okay. By the way, notice the wishbones are a lot more prominent, right? And they're happening all the time because this is a big geomagnetic storm that's occurring all the time. Notice it also tilts. That has a lot to do with the BY component of the field. Okay, the Earth will tilt up, it will tilt down, it will tilt left, it will, dawn, dusk-wise. The Earth's magnetic field can wiggle, especially the tail region, can wiggle quite easily and can go all over the place, which makes Artemis missions quite difficult, to be honest, to try to characterize what they're going to see out there. Because sometimes if they're passing through the current sheet of Earth in the Earth's magnetotail, that could not be good for them. So that's another challenge that most people don't understand that Artemis faces, is Earth's own magnetic field. This is a lot more frustrating area for satellites being in this regime than being in interplanetary space. It's a lot harder on them because it's a lot more dense. But what's interesting about this is that when this satellite comes into a regime like this, where it's poking out, well, we can measure that. Here's GOES magnetometer, and I'll probably stop after this. I'm probably going to go through this just a little bit. This is the GOES magnetometer data. You go to products and data, go back to observations. Not Boulder magnetometer, not the Boulder magnetometer, but where is it? GOES magnetometer. So this is the spacecraft in the geosynchronous orbit. Okay? And you're seeing lots of junk, because there's two spacecraft, not just one. I will show you, at first, just one. Okay, it's a little bit easier. The arc jets, these are areas where you just don't pay attention to the data because things are shifting, because they're doing maneuvers. But notice it goes up, down, reasonably periodic. Oop, there's a little bit of a bigger dip and kind of a recovery. Up, down, up, down, up, down. What's happening here? Oh, haha, cute. What's happening here is that the spacecraft, okay, now we're in the noon-midnight meridian, okay, so here's noon, the other side is midnight, and it's a meridional cut, and the GOES is orbiting Earth, round and round, okay. In this view, GOES would go around like this, because we're seeing in the equator. Here, it comes out of the plane of the page, out toward dusk and goes back into the plane of the page and disappears to the dawn side and then comes back out. So it's, coming out at you, and then it disappears in, and then it comes back around and comes out at you. Okay. So what it's doing is that it's going from the day side of Earth to the tail side. The day side of Earth is crushed, right? This is supposed to be a nice, pretty dipole magnetic field. It's not. It's crushed by the solar wind. So if it's crushed, magnetic field gets stronger. You compress magnetic field, strength goes up. And then it goes around to the night side where it's being elongated. Well, you stretch magnetic field and it gets weaker. Okay. Strong, weak. Strong, weak. Strong, weak. Seeing a pattern? Strong, weak, right? Isn't it interesting that it's strong when it says N and it's weak when it says M? Noon, midnight, noon, midnight, noon, midnight. This spacecraft is going round and round from midnight to noon, back to midnight again to noon. Okay, night side of Earth's magnetic shield, day side of Earth's magnetic shield, night side of Earth's magnetic shield, day side of Earth's magnetic shield. Okay, and it continues to do that up and down. So what you should be seeing is a fluctuation. If everything's quiet, see a fluctuation on a normal 24-hour cycle, because is in geosynchronous, and every 24 hours it makes a full cycle. Okay, when there are anomalies, things happening, space weather events, you see deviations from this pretty periodic motion. Okay, substorms occur, and we'll talk about these more later. Substorms occur with these little bumps and wiggles. And we'll talk more about how that is and what that means and how you can use it to your advantage, depending upon where you live. We'll talk about that later on. And I might as well just show you this one. And if there are two spacecraft, then again, noon, midnight, right? Color-coded. Noon for the red, noon for the blue, midnight for the red, midnight for the blue. Okay? These are spacecraft, or satellites rather, in geosynchronous orbit that are spread out by a certain angle. And so they're both following in the same orbit, chasing each other. So as you can see, this one comes first and then followed by this one. This one goes through noon first, then this one does. This one goes through midnight first, then this one does. Okay? So they're in slightly different places, so they're going to see slightly different things, but still reasonably up and down, up and down. Arc jets, again, don't pay attention to that. That's why they're labeled, because that's where the spacecraft is doing something and you can't trust the data in that area. Okay? But there are certain things, like substorms, that can make a big difference. You'll see a lot more of them during midnight than you will during noon. But there's one other thing. What happens, see, like right now we don't really have any big CMEs, so you have this really nice pretty pattern. And if I go to a 7-day, you see even better. Ah, look, there's something hit, right? Not very big, but enough to give us a nice, we're getting away from midnight, but that looks like a pretty decent substorm. So if anybody saw a decent substorm back on September 4th, which I know we did, there was a little bit more than that going on, but we had some pretty aurora at that time, and a couple other places as well. Okay. But you should always be able to take a look at the magnetometer data on board goes and know where midnight is and know where noon is. Noon is where it peaks, it's the strongest. Nighttime, midnight is where it is the lowest in strength. So you're looking at these nanotesla. Okay. Now, there is something to watch out for, especially with strong storms. No, I had it right. Okay, there's an example there. Same thing. What about this? I'm only looking at 3 days, so I've stretched out the peaks a little bit. So you still see noon, midnight, noon, midnight. The scale has changed a little. Okay, why? Holy manoli, what the heck is this? Okay. In fact, you can see here, you got a big compression up near noon, especially. You see a little bit with the spacecraft that's trailing noon, right, the blue one, but the one that was closer to noon got a big compression. And then a wiggle got up about noon, and then, everything broke. Did the spacecraft die? What happened, and this was for those who are paying attention, This was August, the big August event. It's here. This happened. The spacecraft, the magnetopause, crushed in so much that the spacecraft found itself, did I say that right? Found itself shocked in the magnetosheath, which is the area in front of one. And this may be the magnetosheath. I may need to be careful. I'm not exactly sure with this model what part of it they're modeling and what part is this pristine solar wind. I think this is still the solar wind. And so you've got shock plasma in here, and that's what all this stuff is. But so you're in the magnetosheath in this region. And the magnetosheath strength is way different. And everything goes wacky. Okay, because you've got really compressed field, because what's happening is it's plasma that's being shocked to try to get around this obstacle. It's trying to move around this massive obstacle, and it's supersonic. It's going faster than the speed of sound for this medium. Take that with a grain of salt because it's electromagnetic, so it's not the same as acoustic waves. But we do have sound speeds. We do have sound waves in space. They're just different. Nonetheless, the shock waves form for the same reason that they form in air, is because you've got to get that stuff around the obstacle. And it means you heat and compress and change the direction of the flow. Well, you also increase the magnetic field strength. And so when you see this stuff, that's what's happening. Okay. And as you notice, we were near noon, so if that's going to be noon between blue and red, then noon to noon would be here. So this spacecraft, both of them jumped out when the red one was essentially at noon and the blue one was coming up to noon. So they're both on the day side. Okay. If you see something weird like this when they're in the tail, that would make me kind of go, But on the day side, you get really strong. If the spacecraft are on the day side, you can get really strong breaks with really strong storms. Okay. And what you'll see is a bunch of hash. It'll just go, and then it'll move around back into the tail, and things will look more normal. They'll be crazy because it'll be solar storm related, so things will still be nuts, but it'll be smoother. And then it'll move back out of the tail and more into the day side again, and then you'll see if it's still going on, you'll pop back out in the magnetosheath. Okay. Usually you don't see that very often. You'll see that when there's big storms. You'll also see it when maybe once right when the big storm hits and it really crushes the magnetosphere. Then the magnetosphere recovers a little bit, and then usually you're not slammed like that. But in a Carrington event, yeah, you'd see that. In a big event, you'd see that. I wish I had looked at it during the G5. There were so many other things going on. I don't think I have a copy of what it looked like in the G5, but I'm sure we saw this multiple times. Is it, did it damage the spacecraft? No, not at all. Of course not. Okay, and with that, I'm not even going to get to DRAP today, sadly, because I've been on here for almost 4 hours. Good night. I can't believe I wasn't able to get through. I hope you don't mind me going slow. How many slides did I have left? I did pretty well, though. I went through 40 slides. That's pretty good for me. I have 20 left for this set. Dang. Sorry, guys. So this is going to have to be a two-parter for the basics. So we got through solar, interplanetary, and magnetosphere. And now we're going to go into the ionosphere and down to the ground. So anyway, any questions? I guess first let's open it up to questions on the data products I just showed, the magnetospheric data products. Okay. First we'll do that, and then I'll go into an open Q&A for a short while until my moderators tell me, button it up, we're tired. Okay. Yes, the magnetotail region always points away from the sun, just like a comet. The tail of the comet always points away from the sun. Why? It's got the solar wind blowing at it. It's just like your hair. Is your hair ever going to blow upwind? No, it's always going to blow downwind. Is your scent ever going to carry upwind? Not really, not unless the wind stops, right? Same thing out in space. The solar wind is blowing, and it's always going to be the wind that you feel out there is always going to be from the sun out, away from the sun. Yeah, saw your first aurora on the plane, May 11th. That's right. That's right. When it went back up to a G2, I thought it was going to be waning and I wasn't going to see it, but we ramped back up to a G2 and I watched the whole thing expand and come at the plane, and I got to see it from dusk flying all the way through to dawn. So I got to watch it all change. It was just fundamentally mesmerizing. So I was really grateful that my first aurora was on a plane and I got to see, a synoptic view of it. It was quite magical. So, okay. Caught in the bow. Yeah, are you talking about the Earth's magnetic tail? If so, that's a good analogy. It's been great. Steffi, you appreciated it? Good. I'm so glad you guys liked it. Fantastic. Kat says fantastic. Jared Orby says fantastic. I don't know, Vivid Magic, but feel free. Don't feel like you got to lock in. Just, go potty and come back. I promise I won't hear it. I won't say anything. It's fine. Mike, you think it's okay? I was very thorough. I appreciate that. Okay. Yeah, Metal Halo, you're here to stay the distance. Very cool. Okay, let's see. You appreciate going through this. You're welcome, Elizabeth. I hope this is helping, right? The doctor's saying that everything is changing. Nothing you know is worth anything anymore. Well, I wouldn't say that. Things are changing, but that doesn't mean nothing is worth. What it means is that you have to be careful which things, as things change, you have to change with it, right? So certain things that you know are fundamental, you can hang on to, and certain things you must discard as the changes come. And so, that's one of the reasons why, just even for this course, I use that methodology, because I want to teach you just the basics right now, because I know the data products that I'm showing you are ones that are going to be there. They're going to remain there because they are workhorses of this community, of the solar, the space weather forecasters. And so these ones aren't going to disappear. Some of the ones when we go into the deep dive might disappear, okay, over time, or the missions might go away. But that doesn't ever mean that the physics, the underlying physics that you learn from these data products disappears. No, that's a fundamental truth. So no matter what, even if you feel kind of discouraged that some of these data products are going to go away, or that things are changing, like Earth's magnetic field is changing so rapidly that we have to throw the baby out with the bathwater, no, you don't. Because the fundamental physics will remain the same. And you will be able to build on that no matter what. No matter what our Earth does in terms of, having just a magnetic excursion, or even if it goes to a quadrupole field, which you'll probably never see, you'll be dead. You'll have to be handing this down to your kids. But even at that, the magnetic processes still occur. It's just that instead of occurring two places, the North and South Pole, where a lot of the fundamental fun stuff comes from, we're going to have multipoles where this is happening. We're going to have multiple magnetic tails. Wow, imagine that. Instead of just one magnetic tail, we're going to have several of them. Instead of just one place where aurora precipitates, the particles precipitate in and we have aurora, we'll have multiple auroral ovals, not just north and a south, but a north, south, east, west auroral oval. Wouldn't that be cool? But the fundamental physics still remains the same. It's just that it becomes a little bit more complicated because now you have the interplay of all of these things together, right? But space weather and space physics in general, and heliophysics in general, is going to become very interesting over the next couple hundred years. It's going to become far more mainstream because we use magnetic fields for everything. And if we really are going through a magnetic reversal, there's so much that needs to be, calibrated and followed very tightly as things change, because magnetism rules everything in space. It really does. So we have to pay attention to the magnetic field. We have to follow the magnetic field. Okay. Slow is great for those of us who are slow learners. Thank you, Teresa. I appreciate that. Does the Earth navigate through all of this? Yes, the Earth does. It's been doing it long since before we were born, and it will continue to do so after we're all gone. So you don't have to worry about it, especially if the crazy people on YouTube have a tendency to try to make you scared to the point of paralysis. Don't believe them. Don't believe them. Okay, yeah, that's a lot of, it's okay, a lot of info, a lot to digest. Yeah, I was beginning to notice that too, Kim, so I appreciate that observation. Watched this many times, so much good information to take in. Yeah, I really didn't want to, and Ava, I see this, thank you, you're so kind to explain all this. I did not really want to jump into data products for a long time. A lot of people asked me to jump into data products early on, and I just didn't feel comfortable doing that until I felt that I at least had gotten other mini courses out there for you to look at. And likely I will need to go back and do a bit more on the solar dynamo, sunspots, and things like that, because I think that was one of my earliest courses, and it really, I don't think I did it justice back then. I was just starting out with these mini courses and just kind of learning how to do it all. So I think I will eventually do another course on that and kind of add in some of the new stuff that makes things easier and to understand, and also go into more detail than I did in that course. But that's for the most part, I've got the courses, the basic fundamental phenomenology courses that you will need to be able to fill in the holes if I'm not able to here. Like I can refer you to this, that, or the other one, as Mike and Jerry have also been doing today. Vivid Magic, I don't know. I don't know when you came in, so I don't know when you what you missed. But it's going to be up for forever. This is just the beginning of a long series, so you'll be able to always catch it. Okay. Any questions, guys? Now I'll take questions on anything, because it looks like nobody has questions on the data products at this point, which is nice. So we'll just do a couple more minutes of general questions, and then I will bid you adieu, because I'm sure we're all exhausted after 4 hours. Okay, I'm not going to answer questions about the pull of other planets in this particular mini course. It's just way too far off topic. There's a lot of arguments as to whether or not the sun is influenced by tidal pulls of other planets, especially the gas giants. And some people, it's a hotly debated topic. Some people argue that the forces just aren't strong enough. Some people argue that the forces are strong enough. I have a tendency to believe that the forces are likely strong enough when we look at the right forces. Again, we have Rossby waves on the sun, and that type of dynamics has not been looked at in terms of solar, dynamo dynamics, and even not even the solar dynamo, but just rather rotational dynamics and fluid dynamics in the convective zone. And so I don't know if we understand that, because those types of forces play a role in the dynamics at Earth, right? Tidal forces do. So it's hard to say. It's hard to say. But sadly, I'm not a solar physicist, so I will probably not be the one to do the research. I will be cheering those on who do, however, and I know a few of them, and they're beginning to look. So it's going to be a neat time for the field. Okay. Earth's magnetic field is felt many, many times down through human evolution, maybe influencing evolution. Possibly, yeah, very possibly. I believe that is just the sun in general has influenced human population and how we look at it, depending upon how you look at, if you look at the sun from how it's affected science and how it's affected our lore, just being at low latitudes versus high latitudes, and how differently the sun behaves from those perspectives. The mythology and even our science is different. So it's an interesting anthropological research project. You could write a whole treatise on that. But that, again, is outside of the scope of this, but it's fantastic. Yeah, thanks, Jerry, for putting that up. I appreciate it. Okay. I'd like to see those chart slides next time. Those look intense, like numbers 47, 50. 47. Oh, nah, that's not. That's May 10th. The difference between KP and different Ks. So planetary K versus K in the North American continent, these different locations. They talk about that, and then we're going to go into, after that, we're going to go into K indices and HP. So HP 30, HP 60, these are things that I'll talk about. So that was one of them, 68, 69, 70. What areas are those? See how I indulge you? What did you say, 68, 69, 70? Oh, that's in my supplemental. I won't be going through those. I decided to keep the AE index, this was just the AE index. I'm going to keep that for a deep dive. That's another one that we look at on the ground that's very useful. But it just was proving to be too much for the basics. So, even though it's a very, very well-known and very robust index. Okay, have you written a textbook yet? Lisa, no, I know, I need to. I just need to clone myself, sadly. But there's something in the works, so that I have to talk to my VIPs about that. But there's something in the works, so just be patient with me. Just what I missed while peeing. Cute. You can rewind. That's what rewind is for. Okay, guys, what else? As you go back through the mini courses, what do I do if I have questions? Ask. So if you go back through the mini courses, well, the easiest way, of course, is if you are on Patreon, you can see me every Friday for, my gosh, I'm supposed to only be on for an hour, but I always stretch it out for several hours. You can see me on Patreon and you can talk to me, and I will answer those questions. I'll even go back to that particular mini course and find out exactly what it is that you're questioning. That's why I actually did that. During Solar Maximum, here's the real poop. What happened is that I would typically do a mini course every month, right, for my patrons. And as we reached Solar Maximum, it just became impossible. There were just too many people pulling me in too many different directions, too many forecasts I needed to do, too many things I needed to update and work on the side and give advice for I do stuff in an advisory capacity for certain people and certain agencies. And so it just got to be overwhelming. And so I told my patrons, I said, well, I can't do a mini course every especially now with the mini courses, because I'm having to build them from scratch because I'm beyond what the SWN courses could give me. And so I have to build them from scratch. And so it's like I do one every couple months, but what I gave them instead was a Q&A. A literally live Q&A where we sit in a lecture room, so to speak. It's like a Zoom room. And we talk whatever they want to talk about when it comes to space weather. So that's one really great way of getting me. But you do need to be a member of Patreon to do that. Other ways is that you can sneak questions in during this series. This is going to be a good time to ask specific questions. And if it's not in a mini course, or if it's you tell me that you had a question about something in the mini course that I didn't explain well enough, so just going back to watch it again is not a good enough response, then I will see if I can figure out what the hang up is in terms of understanding, and see if I can explain it to you differently in a way that is more intuitive for you. Okay, so there's lots of ways to get a hold of me. Yeah, Jerry, I see you. Okay, guys, let's see. I've got a couple big ones that people have highlighted, the Dr.Tamitha Scove. Well, wait a minute. Hey, Destruction Warehouse, do you have a lighting sponsor? No, I don't. My wife works at a photo gear company. We could totally hook you up with some goodies if you want. Hey, yeah, sure. It depends upon what you want in exchange. If you want big commercials on my YouTube channel, that's probably not necessarily something I can do. I try to keep those YouTube forecasts reasonably commercial free, because there are a lot of people who watch them for the services, not for ads. I'm not trying to monetize that stuff. So we can talk about that later on. But thank you. I appreciate the offer. So yeah, you can ping me at my Gmail account that's on the YouTube channel. You'll see it. You're very welcome, Treespire. Appreciate that. Great part one, Nick. Thank you. Oh, that's right. I didn't check on Patreon. Let me check on Patreon really quick to see if anybody asked questions there. Cosmological Archaeology Home Planet. Yes, that's a beautiful name for that. And I'm very much interested in that. And if you have references or places that, particular things that you've watched that you really like, or books to read, I'd love if you throw them in there so I can look at them. Len, you said it's going to be a winner. Jesse, you say, what is AU in space weather? Oh, it's astronomical unit. I have a geology background where it stands for gold. Oh, cute, of course, in the periodic table. But I see it in the donkey charts, and I'm pretty sure it doesn't mean gold. No, but that's cute. It does. It does mean money. 1 AU is the distance between Sun and Earth. So when you get to that distance and you hit Earth, money. So that's maybe how you can remember it as AU. I've never even thought about the fact that it's AU on the periodic table. But that's great. I'm going to use that now. So thank you for that. That was cool, Jerry. Or Jesse. That is so funny. So yes, so hopefully that answered that question. Okay. Any other final last second questions. Home Planet, you're saying University of California has a new policy about research. Lots of good for corporate, no secrets, better for the big questions. Yeah, agreed. A lot of UCLA is my alma mater. So, is the sun responsible for the warming on Earth? Are you talking about climate change? You know, climate science is hard. I always say that first. Do I think it plays a role? Yeah. Do I think we understand the role it plays? No, I don't. I think we have a tendency to not overemphasize anthropomorphic effects, because I think we have them. And I think they do play a massive role, but I do think we can't underestimate the sun and take it and leave it out of the equation, because it's not a light bulb. It's much, much more. And as we understand more about the solar cycle and how it works, we're beginning to notice, if we use the solar clock, for example, and terminators, and a new way of looking at solar max and solar min. Instead of looking at the peaks of the minimum and maximum, we're looking at what they call the terminators, which to me is how I look at it is the maximum rate of change. If you're looking at the maximum rate of change, so in other words, what we call the first derivative. If we were to look at the first derivative of sunspot numbers, or first derivative of all the bright points and all this kind of stuff, and we saw that rate of change where it maximized, which just so happens to be at these terminators, that is where we see the biggest change in Earth's climate. And it always seems to be that way, where it's not the peak of something, but it's the maximum at the fastest at which it's changing, right? If you want an analogy of that, think about a pendulum swinging, right? Its peak is where it stops moving, right? It peaks and stops here, and then it swings and it peaks and stops here. And this is why we've been typically looking at solar max and solar min. We knock on where it stops, and then we knock on where it stops, right? So let's say solar max, solar min, solar max, solar min, and that's how we've labeled it. When where we should be looking is at the peak of the speed, where it's changing the fastest, which is at the bottom of the stroke. Swinging up, swinging down, swinging up, swinging down, right? Swinging up into solar maximum, swinging down into solar minimum. Where it is moving the fastest, where the change is occurring the quickest, that's the key to understanding how the solar cycle affects Earth and climate. And I've been a proponent of that since I started aerospace, because I've watched how it worked in the magnetosphere. And it sure see, because I had the expertise with the sun and the interplanetary medium and space weather, and then I got the expertise in how the space weather affected Earth. And I noticed that when we were moving through these things the fastest was when we had the most effects at Earth. And that's when it got me into Scott McIntosh and Bob Lehman, because they were looking at terminators, and they were looking at the sun in a different way. And I said, hey, your terminators are right about where things are ascending and declining during the ascending and declining phases. That's kind of where your terminators and your pre-terminators were. And I said, that's very similar to what I'm looking at, what I'm seeing. So I got onto their work back in 2014, 2015. And I've been a proponent of the work ever since, because that's the key. And so as we begin to do that more, I think we're going to be able to link more with terrestrial weather and climate. But there's still so much work that has to be done, and so much of the fields that need to be melded together. And that's what all of this work is. That's what I'm trying to do, is I help build a field of operational space weather and get meteorologists and space weather folk, heliophysicists and meteorologists to work together in tandem and share their knowledge pool and their expertise. That's why I'm doing this. That's why I do a lot of this stuff that I do, even behind the scenes. SWEN program, all of that. So hopefully that answers that. And with that, guys, I think I will let my very tired moderators get a break. I appreciate all of the questions, and if you did get your question answered and you are a member of the Patreon family, just post it or see me on next Friday, and we'll talk it out. If you aren't, either join Patreon, become part of the Patreon community, or hang on to that question until next time. And we'll have another mini course here soon, and we will dive back into the things we weren't able to finish here. Okay? All right, guys. Oh, Lisa, yeah, Scott McIntosh will be there tomorrow. Yeah, yep. That's cool. Is he talking to Aurora chasers, I take it? That's cool. He's talking to ham radio operators the other day, so it's awesome. I'm trying to populate him, make him make the rounds and get more into citizen science and understand what the space weather community on the ground is, what the boots on the ground are. Yeah, that's me trying to trying to help them in there. All right, guys. You're welcome, Jerry, and you're welcome. Thank you, Mike. Courses are usually every 4 to 6 weeks. Usually, yes. Yes, yes. Okay, guys, have a great day, and we'll talk soon.